Hello, all.
What's going on, bro?
I'm just trying to figure out what's going on with basketball, man. Everybody's getting hurt. Everybody. Giannis is down. Trey Young's down now too. At least the Suns made it past, I guess.
Yeah, I saw that cheap shot that that one guy gave to Chris Paul last night.
Yeah, Pat Beverly. I don't know. Like it used to be like part of his game where he was like defensive and he was just kind of a dog on that side, but now it's kind of just getting out of hand. There's way too many shenanigans now. It's gone past like just the instigator, and now it's kind of just it's too much drama with him.
Oh yeah, I think I saw at least maybe like probably 7,000, maybe like one quarter. I think.
Yeah. The only good thing I saw was apparently Giannis's knee does not have structural damage, so I'm not sure when he'll come back, but he's not crippled at least. That's good.
Yeah, and that one guy's nose too, though. You saw that?
Yeah, Devin Booker's nose the guy. I don't know, man. It's been just a weird year for the playoffs.
Yeah.
All right. Welcome back, everyone. How'd that related rates homework go?
For the half of it that I did, it went fairly well.
Okay, I did send out a quiz. So see how that goes.
Yes, sir.
And I asked you to try all of the problems. They're, I guess those are all kind of like medium level problems. I think the first one, I don't remember the first one.
The balloon, will you
Balloon, yeah, that's kind of straightforward. See how they go. See how they go. And like I said, you can work together. So you'll have to figure out how to do that. You want to meet outside of class somehow, you can. Okay, so last class, what we were talking about at the end, and I think we were all kind of exhausted from the related rates, was derivatives of exponential and logarithmic functions. So I want to make sure that we, are very clear with those new formulas for derivatives. So let me start out with the general formulas from last class. We discovered that if you have y equals a to the x, that the derivative of that will be a to the x natural log of a. That's the main formula. That's the general derivative of an exponential function. Now, because of the chain rule, I want to kind of present this in a slightly different manner. If y equals a to, let's say, some box, whatever it is, maybe it's, a to the cosine of x or a to the x squared plus 1, whatever's up there, when we have to take the derivative of this, we have to apply the chain rule. So first you're going to get a to the box. You're going to multiply that times natural log of a, just like you did here. But you always have to tack on to the end of that the derivative of whatever was in that box. Now in your formula sheet, it looks like, well, let me show you what it looks like on the formula sheet. This is what it looks like on the formula sheet. The derivative with respect to x of a to the x is a to the x natural log a. That's great, but it doesn't really illustrate the chain rule. And so that's what I'm trying to illustrate here is the chain rule.
It just doesn't
Okay.
pop up because the derivative of just x by itself is just 1. So
That's right.
Okay.
Because in this formula, when you do this, if your box is x, then the derivative of x with respect to x would be a 1 out here. And that, so we don't see it, but it's always there. So we have to pay attention to that. Now below this, I want to do the same formula, but for the very specific case that we're looking at e to the x. In that specific case, the derivative of e to the x is exactly itself, and that's it. However, if you have e to a box, then the derivative of that is going to be e to the box times the derivative of the box. So again, you have the chain rule. So I would be looking to try and, I don't know, memorize. I don't know if I want to say memorize. I want you to be looking at it from this perspective more than the way it's presented on the formula sheet, because it's very likely you'll forget the chain rule if you do it that way. Now, when it comes to logarithmic functions, what I gave you last class was what the derivative of the natural log was. So I told you last class that if you have y equals the natural log of x, that the derivative of that will be 1 over x. And I believe that's where we stopped class at that point. But if I generalize this to include the chain rule, then it looks like this: natural log of a box. And remember, that box is kind of like inside the natural log. Then the derivative of this will be 1 over the box, whatever was inside. So 1 over this times the derivative of the box. And sometimes it's easier just to write that as the derivative of the box over the box. So if you ever want to take the derivative of the natural log of something, the answer is just the derivative of that thing divided by that thing. That's what the derivative of natural log of something is. And that's why you have a 1 on top here, right? Because if we're taking derivative of natural log of x, the derivative of x is 1, and then you put it on top of x itself. What I did not share with you last time is what's the derivative of a general logarithmic function. This is the very specific natural log function, but what about just a general log function? So what if you're given y equals log of some other base, let's say base a of x? Well, the book is going to say that the derivative of this is 1 over x times the natural log of a. That's the formula that you'll find on your formula sheet. So look, it's very much like this, right? Like it's very much like this, except that we have to tack a natural log of a onto the outside. Here, when we do the natural log of a, well, what is the base of the natural log function? Do y'all know what the base of this log function is?
Isn't it always assumed to be 10? I think it was.
That's log. If you write log of x, that's base 10. So this really means log base 10.
Ln, isn't that base of e?
Ln is base e. So do y'all see how this formula works? If we did log base e of x, then this would be 1 over x natural log of e. But what's natural log of e? 1. So that's why we get this. But that's only in the specific case that you're doing the natural log. So this is the more general formula. But again, I want you to look at this way. If you have log base whatever of a box, and remember that box is inside the log, then the derivative of this will be 1 over the box times natural log of a times the derivative of the box, which can be rewritten again as the derivative of the box over the box times natural log of a. So just slide that on top. So if I were you, I would be thinking of these as opposed to the way it's presented in the book. Does that all make sense? Any questions on that? I want to do an example just so you can see. Oh, before I do that, let me just off topic, but kind of on topic. In college algebra, when you're being taught about logs, you're told that a log function, right? When you're presented this idea of a log function, you're told that this base here is just a number, right? You're told that that has to be greater than 0 and it can't be 1. And then you're told that you could pretty much have a bunch of different types of logs. You could have log base 2, you could have log base 3, you could have log base 10, you could have log base a half, you could have log base e. You know, there's an infinite number of log functions you can have. The two most important ones are log base 10 and log base e. Those are the ones that occur for us most often. Now, log base e, we don't write log base e as log base e. We write it as natural log of x. We write ln. This is an L and that's an N. It's not an I and an N. It's French. Logarithm natural. Okay, French, they do it backwards. So it's logarithm natural. Okay, natural log of x. And then this right here, base 10, is another important log. So instead of writing it log base 10, we just write log x. So it's kind of like when you do a square root, right? Square root of 4. We all know that that's the square root, even though it's not written as a 2 here, right? We know it's a square root, not a cube root. Same thing. When you write log x, that means log base 10. When you write ln x, you mean log base e. And I personally have always found this to be a problem when I'm teaching it, because I wish we didn't do that. I just wish we always wrote the base, no matter what. That's the way I wish it was, because it makes these look somehow different than what the others are. But you know, they all have some base. So when I was a student, I was very frustrated with that, and teaching it has been frustrating too. But there's a historical reason why we do it. Okay, there's a reason why we write these this way. And the reason is that, you know, if you're doing, like, think about chemists or biologists or physicists, mathematicians that have were doing research, you know, back in time. Just go back in time a bit, and they're doing research and they're doing these papers, and maybe they have this 500-page paper where they're explaining their work, and within their work they have, you know, a log base 10, and natural log is within their work. Maybe it appears hundreds of times. Okay, well, back in the day when people were using typewriters, you don't know what a typewriter is? Okay, I'm sure most of you have never used a typewriter. I think I did when I was in grade school. But a typewriter is basically a machine that you hit buttons and it physically like stamps the paper, right? These little things go and hit the paper. So if you're typing, if you wanted to type log base 10, you have to subscript the 10, right? So how do you subscript on a typewriter? Well, you type and then you have to turn the drum and then hit 1, 0, and then turn the drum back and then hit X and keep going, right? So if you had to do that hundreds of times within your paper, it would just be a pain in the ass. So they just said, all right, if you're doing log base 10, do log X. If you're doing log base E, do ln X, and we'll understand what you mean. And you don't have to stop typing. You can just keep going. Does that make sense? It's just to speed things up, all right? Unfortunately for us, I think it makes things confusing, right? It's still even hard to subscript in a word processor, isn't it? Like on, I mean, I'm sure there's a shortcut key to subscript and superscript when you're typing up a paper, but it is easier than a typewriter because you don't have to physically like move anything. Okay, that's off topic, but I thought I would just share that with you. All right. Okay, so I said I want to do an example. So let's do an example of a derivative with some log stuff in it. So let's say I give you y equals, let's say log base 3 of x tan x. And I want you to find the derivative. So what we have to understand here is that we have log of a box, right? There's our box. And it's log base 3. It's log base 3. So since it's log base 3, I know that the derivative will be 1 over the box, which is x tan x, times, now I have to include this natural log of a. So natural log of what?
Of 3.
3, right? That's just a little number. It's just a little constant that I have to include in my derivative. And then times, now I need the derivative of the box. So I'm just going to write it down here. I need to take x tan x, and I still need to take its derivative. I haven't done that yet. So that's why I put the little prime mark there. And then that's going to become 1 over x tan x times natural log 3 times, now that's a product, so I have to use the product rule, 1 times tan x plus secant squared x times x. And of course, I could maybe like get rid of the 1 and maybe put this x in front of the secant squared and then slide the whole thing on top and be done, but I'm just going to leave the answer like this. Any questions there? I can't help myself. Oh, go ahead. What's that?
So how did you get the 1 over x tangent x times natural log 3 for the derivative?
So that is what the derivative of any log is. So if you have log base a of x, or of a box, the derivative of that is always 1 over whatever was there times natural log of a, always. And then you have to tack on to that the derivative of what was in here. Is that what you're asking?
Yes, sir.
Okay, so for us, our box was x tan x and a was 3. So we just put 1 over x tan x natural log of 3, and then we still had to take the derivative of the argument of the function, which was the x tan x.
Oh, I see.
You sure?
Yes, sir.
Okay, everybody see that? Okay. Let me just pick a random problem out of the book here. Okay. Y equals, I might modify this problem a little bit. Tangent of natural log of x squared plus 3x plus 1. Find y prime. So what we have here is composition. We have x squared plus 3x plus 1. That's all inside of a log, right? This is not multiplication, this is composition. So this polynomial in yellow is sitting inside of a natural log. But all of that is sitting inside of a tangent function. So we have a triple composition, which means we're going to need to use the chain rule. And we always need to start from the outside and work our way in. So let's see if we can handle this. Can somebody give me the first part of this?
So you're gonna have secant squared of ln of x squared plus 3x plus 1.
Secant squared of, so you said, let's take derivative of tangent of something, right?
Mhm.
Which is secant squared of everything in there.
Yes.
Good. Okay, someone else want to give me the next part? Multiply that by what? So we
It would be 1 over x squared plus 3x plus 1.
That's right. And you don't need that little natural log thing in there, right? Because it is the natural log function. So we're using that. We're using this one right here. Because it's natural log, all we have to do is put 1 over the box, right? So we just did, okay, derivative of natural log of this is just 1 over it. And then we continue. Who wants to give me the last part?
Times 2x plus 3.
Times 2x plus 3. That's it. And that's the derivative of the yellow part. And we could probably put this on top there. That would be fine, but I think we're good there. Any questions on that? Let's do another one. Oh, sorry, y, not y prime. Let's see if any of these look interesting. Okay. E to the u minus e to the negative u over e to the u plus e to the negative u. And I want you to find y prime, which I mean dy du. So basically, this is an equation y equals this, and it is a function of u. So I'm just using u's instead of x's, okay? We're going to do everything the same way, except we're going to treat u as the independent variable. So when we differentiate, just the derivative of just u will be 1, okay? All right, so what do y'all see happening here?
Well, we got a quotient.
We've got a quotient, right? We've got a top function, f. We got a bottom function, g, right? So we know we need a quotient rule. All right, so we know that the derivative of this should be the derivative of f times g minus derivative of g times f all over g squared. It's going to be a mess. Let's start with the derivative of f. So let me write it over here on the side. Maybe this will help. If f is the top, then f is this, right? Let's figure out what the derivative of that is. Okay, now, let me see. I want to feel like calling on people today. Cruz, you're up. I think we're just going to go alphabetically here. I'll start at the top of the alphabet, then I'll go to the bottom, then top, back up, down, up, down. We'll meet in the middle. Okay, so Cruz, you're up. So Cruz, what is the derivative of e to anything?
It would be on this case, it'll be e to the u.
Yeah.
And then I guess you would tack on the minus e to the negative u already, right? And then just multiply it by the other part, or no?
Well, we have subtraction, right? We have subtraction, so we can do
okay.
these separately.
Oh,
So-
okay.
Yeah, so just the derivative of e to the u, okay, that right there is just itself, right?
Mm-hmm.
Okay, now you have to be a little careful because you have to also pay attention to what's up here, and you have to take derivative of what's up here. But Cruz, the derivative of u will be what?
1.
1, okay, because the derivative of u is 1 because we're treating u like x.
Mm-hmm.
So I'll put times 1 here even though we don't need it. The derivative of e to the u should be e to the u times the 1. Okay, minus. Now, Cruz, what's the derivative of e to the negative u? So what's the derivative of e to anything?
It's the same thing again.
Okay, e to the negative u. Okay, now times, now be careful there, Cruz. What's the derivative of this?
Would it just be a negative 1?
Negative 1, right. Okay, y'all see the difference between the derivative of this one and the derivative of this one. We get a negative to pop out here because derivative of negative u is negative 1. And if I clean that up, I'm going to get e to the u plus e to the negative u. Because the minus and then the negative become a plus. Good, Cruz. Let's see, Alejandro, are you here? I know
Yes, sir.
you've already participated, but we're just doing scratch work on the side. How about you help out with G? So G is the denominator, e
Mhm.
to the u plus e to the negative u. That's the bottom. What is that derivative, Alejandro?
It would be e to the u plus, or no, it's times
No, it's plus,
plus.
no product because this is addition, right? So you're just going to do them separately. Derivative e to the u is itself plus now the derivative of this.
Would it be -1?
We'll have e to the negative u first, right? You have to just say itself and then times the -1, right?
Yes.
Okay. Is everyone clear on that? Are y'all sure? Okay.
I'm a little about that.
Okay. Well, let's talk about it. The derivative of e to the u is itself times the derivative of 1, which, I'm sorry, the derivative of u, which is 1. So I didn't put it here. There's times 1. Is that what you were saying?
Yeah, that's what I was trying to say for the first
Okay,
one.
I'm sorry. I thought you were talking about something over here. Okay, so derivative e to the u is itself times the derivative of u, which is 1, plus the derivative of e to the negative u, which is itself, times the derivative of negative u, which is -1. That make more sense, Alejandro?
Yes, sir.
And then just move that minus out here and make it a subtraction. So now we just put it all together. So we're gonna have y prime equals, okay, f prime first. And that was our f prime. So it's e to the u plus e to the negative u. We need to multiply that times g. G is the bottom. E to the u plus e to the negative u. And then subtract from that g prime, which Alejandro just got, e to the u minus e to the negative u, times f, which was the top, e to the u minus e to the negative u, all over g, which is the bottom, e to the u plus e to the negative u, all of that squared. Okay, now that is the raw derivative. Are there any questions on the raw derivative? I'm going to clean this up because there's some stuff in here that happens that I want you to see. All right, so I'm going to multiply here to here first. I'm going to FOIL these and FOIL these. So when I FOIL, what's e to the u times e to the u? E to the u times e to the u. What do you do there? Same base, multiplying together. What do you do with the exponents?
You add them, don't you?
Add them. And u plus u is 2u. So that first multiplication we get there is going to be e to the 2u. Okay, now let's do the next multiplication. This is the one that's kind of cool. What's e to the u times e to the negative u?
E to the 0,
E to the 0. And what's e to the 0?
1.
1. That's weird. Plus 1. Now do this one, the middle one. E to the negative u times e to the u. What are you going to get there?
1.
1 again. Now the last multiplication, here to here. That's e to the negative u times e to the negative u, which is
E to the negative 2u.
negative 2u. Because you add them up, negative u plus negative u. So you get plus e to the negative 2u. Okay, that's just these two multiplied together. Then I have a minus sign, minus. Now I have to be real careful with this minus sign because the minus sign is going to distribute. So let me figure out what all this shit is first, okay? And then I'll put the minus sign through. So e to the u times e to the u, what is that?
E to the
E to the 2u, right?
Yep.
Add them up. What's e to the u times negative e to the negative u? So you add the exponents and you get 0, right? E to the 0 is 1, but you have a minus because this one's negative and that one's positive. So we should get minus 1 there. And then on the middle one, again, e to the negative u times e to the positive u, you get a 0 on top. E to the 0 is 1, but again, it'll be negative because you have negative times positive, so negative 1. And then our last multiplication here to here, a negative times a negative is positive, so I know my answer is positive. And then e to the negative u times e to the negative u is g to the negative 2u. You all right with that?
Yep.
Okay. Now, the reason I did that is because a lot of things are about to cancel. I think, hold on, I haven't really worked this out. I'm out of room. So 1 plus 1 is 2, right? Negative 1 and negative 1 is negative 2. And then I have to distribute the minus through here. So it turns that to a minus turns a -2 to a plus, turns this plus to a minus. And do y'all see all the good canceling?
Yeah, you just end up with 4.
Yeah, so all you wind up with on top is a 4. And on the bottom, you get e to the u plus e to the -u squared. I just wanted to show that to you because that whole thing with the e's and how they become like a 1 and stuff, that actually does come up quite a bit in differential equations. And when you start talking about hyperbolic trig functions in Cal 2, this comes up again. So I just wanted you to see how that simplifies. Okay, y'all good? So I can't help myself. I have to talk about this. I don't know. When we were talking about the logs, I just couldn't help myself but think about this. You know how we have all these different logs? And we say, okay, log base e, that's an important one. The reason why this one is important is, and I told you this last time, is because this natural log function is the inverse of e to the x. So when you put e to the x and natural log together, they kill each other off. They're inverse functions. And I hope that I explained last class that e to the x is a very important function. We looked for it, we found it, we were happy, right? We called it the natural exponential function. So natural log and e are like connected. They're very, very intimately connected to one another. The log function is the inverse. Okay, so this one is the inverse of e to the x. Log function is the inverse of 10 to the x. And 10 to the x is our base 10 exponential function. And this is obviously the log base 10 function. So why do you think the log base 10 function is also very important and comes up a lot in the real world? Do you have any idea why log base 10 would come up so much?
Like when you talk about like, I guess like the distance of like planets and space are like really, really long, or like they're like really, really far. So you don't want to write like 0, 0, 0 and stuff.
Okay, but I mean, wouldn't log base 9 also be, I mean, what's like 10 to the x is just an exponential function where the base is 10, like 9 to the x is another one, 8 to the x is another one, 11 to the x is another one. Why is it that the base 10 log and exponential function appear a lot in the real world math that we do? Why do you think that
Because
is?
our 10 is a base of like a lot of the unit scales we use or something?
Our number system is base 10.
There we go, yeah.
Our number system is base 10. Now I know, I remember when I was a calculus student, if someone were to talk about, you know, our number system being base 10, I had no freaking idea what they meant. I'd heard it, but I didn't understand it. So I'm going to take it, we're taking a tangent, no pun intended, we're taking a tangent. I want to talk about bases real quick. This may not come up, this is not going to be tested, but if you're a computer science major, the base of your number system is critically important, all right? So when we say base 10, okay, when we say base 10, what we mean is that in our number system, we have 10 digits that we use to represent all numbers. So in our number system, the digits we have are 0, 1, 2, 3, 4, 5, 6, 7, 8, and 9. Those are the 10 digits that every number in the base 10 number system can be represented with. So for example, if I write the number 400, let's go 4,351, okay? What we learn in grade school, way back when, and you may or may not remember this, is that, well, you may or may not remember learning it. You're going to remember what I'm about to say. This 1 represents how many ones we have. Ones. This represents how many tens we have. This represents how many hundreds we have. And this represents how many thousands we have, right? Well, what do we really mean by that? What we mean is that, let me see, what's another way I could write this? I could write this as 4,000 plus 300 plus 50 plus 1. Do you all agree I could write it? That's the same number. And 4,000 means 4 times 1,000. This means 3 times 100. This means 5 times 10. And this means 1, right? Just 1? Go with me?
With this, are you trying to say that this is like kind of like bits for coding and stuff like that, with each place
Yeah.
able to
For a computer, right? For a computer only has 2 digits possible, 0 and 1. And that's because within a computer, you either have an electrical signal or you do not. So it's only 2 states that you can be in. So a computer uses base 2 number system. They don't use base 10, all right? I'll get to that in a minute. What I want you to see here is something that, this is the part I'm not sure you've seen. Another way I could write this is 4 times 10 cubed. Isn't 1,000 10 cubed? Plus 3 times 10 squared. Plus 5 times 10 to the first. And then this last one I could write as 1 times 10 to the what?
0.
0.
0. Good. You see that? So every number here, every digit, right? Every single one of these digits is just telling me how many tens to a certain power I have. Anything in the ones position is how many 10 to the zeros I have. Anything in the tens position is how many 10 to the ones I have. Anything in the hundreds position is 10 to the twos. That's how many 10 to the twos I have, or how many hundreds, how many thousands, and so on and so forth. Okay, go with me? Okay, now, this is the way our number system works. We have 10 digits, 0 through 9, but there's nothing stopping you, nothing stopping us as human beings from having a completely different number system. We could have, if we wanted, decided to use base 2. Base 2 would mean there's only 2 digits. And we could have called them anything, but let's stick with 0 and 1 because that's what we know, right? This is 10 digits. We could have used any symbols we wanted. These are the symbols you've learned to represent those 10 digits, right? Base 2, these are the only 2 digits we have. So if I want to write a number, like I gave you an example of 4,351, that's a number in base 10. If I write a number in base 2, I can only use zeros and ones. So if I write, let's say 1, 0, 1, 1, 0, 1, that is a number in base 2. Now, what number is it for us in base 10? Like, what number does that represent? Well, let's do the same principle. Remember how we said that here the 4 represented how many 10 cubes we have? Here's 10 squareds, 10s, and 10 to the zeros. The 10 is the base, right? And the number in front is just how many of them we have. So with that similar argument or similar setup, because this is base 2, I'm going to have some number of 2 to the zeros, 2 to the ones, 2 squareds, 2 cubes, 2 to the fourths, 2 to the fifths, and so on and so forth. And I'm going to start here. How many 2 to the zeros do I have? According to this number, how many 2 to the zeros do I have?
4.
Look at the first, this right here is how many 2 to the zeros I will have. Just like up here, right? The 1 was how many ones I had, yes? Which was how many 10 to the zeros I had. The 5 was how many 10s I had, which is how many 10 to the ones I had. 3 was how many 10 squareds I had. Are y'all seeing this? Mm-hmm. How many 2 to the zeros do I have according to this? 1. So I have one of those, 1 times that. Now that's added to how many 2 to the ones do I have?
0.
0. So I have 0 times that. Okay, that's being added to how many 2 squareds do I have?
1.
1. Okay, how many 2 cubes do I have?
1,
1. How many 2 to the 4ths do I have?
0,
0. How many 2 to the 5ths do I have? 1, right? I have 1 of these. So let's figure this out. What's 2 to the 5th power? What's 2 times 2 times 2?
32,
32. So I have 132 here. So that's 32. Plus 0 times anything is 0. Plus what's 2 cubed?
8,
8. 1 8 is going to be 8. Okay. 2 squared?
4,
4. 1 of those. None of these. 2 to the 0 is 1. And I have 1 of those. So plus 1. Now add all these up. 45. Base 10. Base 2. So a computer will understand the number 101101 as being the number 45. So when I type in 45 on my keypad, the computer is only seeing zeros and ones. That's all it's seeing. Does that make sense?
yeah.
So why, this ultimately, I was getting to this question of why is the base 10 so important? And Cody said, well, because our number system is kind of like base 10, right? Which it is, our number system is base 10. But why did we choose base 10?
It's easier for us. I mean, we can't come up with like a series of 1s and 0s that we can quantify easily in a quick manner versus like 4, 3, 5, 1.
I would argue it's only easier because it's what you've been taught from when you were a child.
I guess that's,
If we had started you off in the very beginning with base 8, you would be telling me that base 8 is easy and base 10 seems foreign.
well, true. I guess I'm just speaking like from the perspective of base 10 to base 2. It's just like the amount of combinations that you can have just for a smaller number versus like,
Cody, you're giving us a hint right now. Why do we use base 10? Why did we choose base 10? What?
More combinations.
More,
you know,
yeah.
say combinations or easier
Think
representation.
about it. Think about it. Why 10?
Because we have 10 digits every single time.
No, we have 10
We have
fingers.
10 finger,
okay.
we have 10 fingers.
We have 10 fingers.
I was overthinking it so hard. I'm like,
I know.
Like
I mean,
the
that's
EM
why though. That's
That
why
makes
we had
sense.
base 10.
it does,
Because
it does.
we
Yeah,
can count.
that's-
I guarantee you that if we didn't have thumbs, we probably wouldn't be here anymore. But you know, if we had, let's say, 12 fingers, we'd be using a base 12 system because that's what we would be used to counting. Okay, everything would make more sense to us that way. So base 10 is just because that's the system that makes most sense to us. If we were to ever make contact with some alien species that had 16 fingers, if they even had fingers, if they had 16 fingers, then I would almost guarantee that they would have some sort of base 16 system. And we do too. We have base 16. We can use base 16, but the problem is when you get to base 16, right? How many digits would you need in a base 16 system? How many digits would you have?
15.
There's 16, 0
16.
through
So
15.
we would go 0, 1, 2, we go out all the way to 9. And then once we get to 9, we can't put 10 because 10 is not a digit. 10 is 2 of our digits together, right? So you know what we start using? Letters. So there's 10, 11, 12, 13, 14, 15, 16. We use letters. Now, let me show you this, I believe is called hexadecimal. If I'm not mistaken, this is called base 16 is called hexadecimal. Let me check that.
Use though, like where would you actually need 16 digit, like a 16-digit number system?
Whenever you're trying to do any sort of, oh shit, what am I thinking here? Yeah, 16, hexadecimal. When you are doing encryption,
Okay.
right? So, you know, when you do like 32-bit operating systems, 64-bit operating systems, that has a lot to do with bases. I mean, it's, okay, I'm gonna keep going. So let me show you something. You ready? This is kind of cool. I'm sorry I've taken 15 minutes now. I want you to see this. So what is this number in base 10? So I'm gonna give you a number in base 16, and I wanna know what it is in base 10. 4CF1. Let's do F3. What is that number? That I'm giving that, I'm telling you that's base 16. I want to know what it is in base 10. So following the same format as before, the base tells us the pieces we have. So the first one's 16 to the 0, next 16 to the 1, 16 squared, 16 cubed, 16 to the 4. I don't know how many of these we're going to need. How many 16 to the 0s do we have?
3.
We have 3 of these. Plus, how many 16 to the 1s do we have? This is weird.
15.
We have F, but F is 1, 2, 3, 4, 9, 10, 11, 12, 13, 14. F is really 15 in the base 10. So we have 15 of those. Plus, okay, C, that's how many 16 squareds we have. So 9, 10, 11, 12. So that's 12 of those. You all understand what I'm doing? And then 16 cubes, how many of those do we have? Well, 4. And then I did too many. We don't need this because we didn't go further. But I could have put more stuff out there. And now I just get my calculator out and do this. So I'll do 16 cubed times 4. So this is 16,384 plus 16 squared times 12. So that's 3,072 plus 15 times 16, which is 240, plus 3 times 16, which is 48. So if I do that, 16384 plus 3072. I'm sure someone here has already got this, but you get
Or wouldn't it be
one.
3 at the end, not 48? 3 times 16 to the 0 is 3 times
Oh,
1.
16 to the 0. Yes, my fault. I got it. I screwed this up. Sorry. This is this right here is 3 times 1. Thank you. That's a 3. So hold on, let me change that. Trying to go too fast. There we go. So 4CF3 is 19,699. To us, base 10, like that's what those letters in that sequence 4CF3 really represents that number. And if you go online, you can do this. Let's see, what was it? 4C,
F3.
F3 hexadecimal to, let's see what it does. Decimal? No. Here we go. Is that what we got?
Mhm.
No, 96. Wait, did we get 96?
Well,
or-
it was 3 at the end, not a 0.
Have 4CF0, not 4CF3.
Oh, yeah, okay. We're missing 3. Thank you. There we go. 19,699. Now, look, we can do this for all sorts of bases. We can go from pretty much, well, this goes from base 32, goes all the way up to base 32, so you can convert. And they have names for all these. Octal, base 8. Decimal, base 10. So our decimal system is just one of an infinite number of decimal systems out there, or bases out there. One more thing, can I show you one more thing? Just one more. I swear, this will be the end. One more thing. What if we write, what was the first number I gave you? I like how I ask you a question that I don't give you an opportunity to respond. 4351. So what if we write 4351.253? Now we're getting decimals, right? And do you remember what you were told about what this represents? The 0.2 is how many whats you have?
Tenths.
Tenths, right? This is how many tenths you have and how many hundredths, right? And all that crap. Well, let's just follow the same thing we had before. If the 1 was how many 10 to the zeros we had, and the 5 was how many 10 to the ones we had, and the 3 was how many 10 squareds we had, and the 4 was how many 10 cubes we had, then what do you think the 2 is going to be? Follow the pattern.
Was it like -1?
Yeah, I was gonna say.
Yes, exactly. It's going to be 2. We have 2 10 to the
-1.
negative ones plus 5 times 10 to the negative 2s, right? Plus 3 times 10 to the negative 3. But what is 10 to the negative 1?
1/10.
110. And what is 10 to the negative 2? 1/10 squared. That's 1/100, right? This is 1/1000. So that's why in grade school you're taught this is how many tenths we have. Well, it is. It's 2 tenths. This is 5 hundredths. This is 3 thousandths. Interesting, huh?
Mhm.
That's also why scientific notation's the way it is, right?
What's that?
That's why scientific notation is the way it is, because it's just.
Yeah, that's why
parts.
scientific notation is so easy to use. It's because every digit here is just some power of 10. I mean, that's all it is. So it's pretty awesome. I think it's cool. There's a problem that I gave one of my colleagues one time, and I asked him, when is 1 equal to 0.111 forever? When is 1 equal to 0.1111 forever? Now, you can't answer this until you take Cal 2, but you can actually show that in some base, if you take this in some base, that it will be equal to this in some other base. I'm not going to tell you because it's not worth us going into, because I can't prove it to you because you need Cal 2 for it, okay? But there is a way that you can say 1 is equal to 0.111, as long as you're making sure you understand the left side is in one base and the other side is in a different base. Okay, back to reality. 10 fingers, huh? All right, so now that we've got this, we understand hopefully how to take derivatives of exponentials and logs. I need to introduce you to a new type of differentiation. Now, this differentiation is, when I first present it to you, you're going to be like, well, that's useful. And then I'm going to show you other problems where you're like, okay, well, then it's actually necessary sometimes. So the problems I'm going to show you where they're useful is like, okay, we could have done it the other way, but this new way is easier. And then you'll see after I show you another example, like, okay, well, there's some problems we have to use it for. So here's an example. All right, so look at this one right here. What if I have y equals natural log? Now we know how to take derivatives of natural logs, right? What if I say natural log of, or no, you know what? Let's not take natural log. Let's forget the natural log. Let's just do this. X squared times x plus 4 cubed times the square root of x minus 5 all over the cube root of x plus 1 times x minus 3 to the 7th power. And I want you to find y prime. All right. So let's see here. Justin, you're up. So if you look at this, Justin, you'd be like, what would you be thinking if you saw that? and I ask you to take derivative, what would you be thinking we should do?
Immediately quotient rule.
Quotient rule, right?
Yeah.
Now, do you see what a disaster that's going to be?
Yes.
Because the numerator itself, right? Even just the top itself is like a triple product rule, isn't it? It's
Yeah.
like when you go to take the derivative of the top at some point, you've got to handle the fact that there's like multiple things being multiplied, right? So that looks right now to be doable, right, Justin? Doable, but not something that you are looking forward to. Would that be safe to say?
Yes.
Okay. So I would like to do something. I would like to consider, I'd like for everyone to consider this. What if I take the natural log on both sides of the equation? Okay, so let's just do it and see what happens. Now, you're allowed to do that. You can always take natural log on both sides of the equation. And let's just see what we would have. We'd have x squared, and we'd have x plus 4 cubed, and then square root of x minus 5 all over, cube root of x plus 1, and then we still have x minus 3 to the 7th. There we go. Now, that step right there is not calculus at all, okay? That is just algebra. I'm taking natural log on both sides. Now, Justin,
Yes, sir.
you okay with that step? You okay with me doing that, even though it doesn't seem very natural?
Yes.
Okay. Now, from college algebra, do you remember, and I know we covered this last class, there are some things about logs you learned in college algebra that allow you to like expand and condense logs together. Do you remember those properties? I mean, maybe not off the top of your head, but do you recall things like if you have natural log of like x times y, you can split it into 2 natural logs with addition? Or if you have natural log of x over y, you can split it into 2 logs with subtraction. Does that seem familiar?
Yes.
Okay,
I
and then we
remember.
had, go ahead.
I remember them existing, but I didn't remember them specifically.
Okay, so these are the 3 big properties of logs that we need to do this problem. First one says if you have a single log with multiplication, you can split it to 2 logs with addition. Single log with division, you can split it to 2 logs with subtraction. Log of something to a power, the power can come out. I showed you all these last class, all right? But I'm going to put them up here because we're about to use them. So Justin, do you see that we have natural log of something over something? So it's kind of like this formula right here.
Yes, sir.
So would you be okay with me splitting it into 2 logs?
Yes.
Okay, so here I go.
Would you then split it again? with
Yeah,
the-
exactly. You see where this is going already. So I'm going to just take the top, put that in its own log, and then minus now a new log, and then everything in the bottom. No calculus, okay? We are not doing any calculus. All this is algebra. This is why when you were in algebra, they asked you they taught you how to expand and condense logs. This is part of the reason why, it's because you need to be able to take a derivative later. Okay, so that's just this first property. Now, Justin, you said something that I could do what now?
You could use the one where they're multiplying right above
Yeah.
what we just used on
Yeah.
both of those.
Exactly. So Justin's saying, look, if we ever see multiplication inside of a single log, we can split it into 2. What if we see 3 multiplications? Split it into 3. If we see 4 multiplications, we split it into 4. So when I look at this first log, and Justin, you're off the hook, thank you. That you marked down here. So Daniela, you there?
Yes.
Okay, so are you following what's going on here with all this?
Yes, I think.
Okay, so on this first log, I have 3 multiplications. Oops. I have 2 multiplications. I have 3 things being multiplied. 1, 2, 3. That should split up into how many logs then?
3.
3, right? And be careful, everyone. I'm not doing a product rule. I'm not taking a derivative. I'm just doing algebra right now. So Daniela, what would the 3 logs be? Natural log of what?
X squared.
X squared, okay, and then what
plus
goes plus? Good. Natural log of
x plus 4,
q,
yeah, cube,
okay,
and then plus natural log of the square root x minus 5.
yes. Now that is a cube root. Did I move the? Yeah, I accidentally put that line on the wrong. Wait, no. It was square root, wasn't it?
Yes, it
Yeah,
was not a
sorry,
cube root. That was
square root. So look, I am going to rewrite that as being raised to the 1/2. Daniela, is that okay? Instead of me writing the square root, I'm going to do the 1/2 power. And everyone, you'll see why I'm doing that in a minute. Is that all right? Daniela, you happy with that?
Yeah.
Okay. All right, let's keep going, Daniela. On this next natural log, do you see the multiplication happening there between those two things?
Yeah.
Okay, so this can split up into how many logs?
2.
2, okay. So it should be the natural log of this one plus the
Yeah.
natural log of that one, right?
Yeah.
But we have a minus sign here, right? We have to be really careful with that minus sign. So watch what I'm doing. I'm gonna do minus, and I'm gonna go ahead and do the property right now. So it'll be natural log of this first one, which I'm gonna write as x plus 1 to the 1/3 instead of cube root. And then plus natural log of x minus 3 to the 7. You all right? Let's get rid of the parentheses. So that means the first one becomes negative and the second one also becomes negative, right? So they're both minuses. Any questions there? Okay, Jorge, do you see what I'm going to do next? Is Jorge here?
Yes. Sorry.
I'm going to use another property. Do you see which one I'm going to use?
The bottom one, the last one.
Yeah, everywhere we see a power, right? Everywhere we see powers, those are like these ends right here, and we can always pop those out in front of the log. So Jorge, go ahead and tell me what I'm going to have on the next line. So pop the 2 out in front. What would you have?
2 natural log x
Okay,
plus 3 natural log x plus 4
okay.
plus 1/2 natural log x minus 5
Yep.
minus 1/3 natural log x plus 1 minus 7 natural log x minus 3.
There you go. Okay. This is still algebra, right? We haven't done any calculus yet. But at this point, look at how nice everything is. We have a bunch of additions and subtractions separating everything out. We have constants in front of functions. So all these constants, 2, 3, half, -1/3, -7, they can all come for the ride. So the big question is, can you differentiate these? Those are the pieces you need to be able to differentiate. And that's what we've already learned, right? We know how to do the derivative of natural logs of things.
Right.
So we should be able to handle each of those. So at this point, we are ready for the derivative. Okay? You ready for it? Pay attention, because I have to use implicit differentiation. Because look what's on the left-hand side. It's not y anymore, is it? It's natural log of y. So I'm going to now do the derivative on both sides. So I'm about to do derivative with respect to x on the left. And then same thing on the right. I need to take derivative with respect to x. All right. Bree, you ready?
Yeah.
Okay. Carefully, Bree, tell me what the derivative of natural log of y is with respect to x. So what's the derivative of natural log of anything, Bree?
1 over x.
Yeah, 1 over
Y.
whatever was there, right? 1 over. But then because of chain rule, what do you have to put next to this?
Times d, or the dy over
dy
dx.
dx, that would be dy dx. Do you all agree with that? That would be next. Now I'm just going to write it as y prime. It's the same thing, right?
Okay, yeah,
That's dy dx. I'm just going to write y prime.
okay.
Okay, good. Equals. Now let's see, Bree. Let's see if you can crank this all. I don't know. Okay, so 2 is in front, right? It's going to come for the ride.
So 2 times 1 over x
Good.
times dx over dx. Is that 1? I don't.
Which is 1. Exactly. Yes.
Okay.
Okay. So everyone, 2 comes for the ride. The derivative of natural log of x is 1 over x times the derivative of x itself, which is just 1. So I'm just going to put that. Good. Keep going.
Okay. Plus 3 over times 1 over x to the 4, or x plus 4.
Plus 4. Good.
Okay.
And then you have to take derivative of what's in here. It's just
Times 1.
1. Okay, so I'm not
Plus
going to write
0.
anything. Is that okay?
Yeah.
Plus
Plus 1/2 times 1 over x minus 5 times 1, which is nothing.
times 1. So nothing. Good. You starting to catch the hang of this?
Minus 1/3 times 1 over x plus 1
Yep.
minus 7 times 1 over x minus 3.
There you go. Now we could at this point put all of these numbers, you know, we could like put the 7 up here and we can mess with it. That's pretty good. All right, good job, Bree. So Naja, are you here?
Yes, sir.
Are you following this?
Yes, sir.
Where are you? There you are. Okay. So Naja, do you see that this is not what y prime is? This is not the derivative. This
Yes.
is y prime times 1 over y, right?
Mhm.
So we just want to know what y prime is. So how could I get rid of 1 over y? What could I do on both sides of the equation?
You would multiply by y.
By y. Y here, and then yes, I'm not kidding. Y goes over here, okay? The y's cancel. You get y prime equals, look at this answer. It's going to be this 2 over x plus the 3 over x plus 4 plus 1 over 2x minus 10. What did I do there, Naja? 3 went up, 2 went up. What happened here?
Oh, you multiplied the 2 by x minus 5.
Yep, so I just distributed the 2 through. Minus 1 over, and I'm doing the same thing here. So 3x plus 3. And then minus the 7 goes on top, x minus 3. Got that, Naja?
Yep.
But we still have to multiply that times what?
Y.
Y. Naja, what is y?
The x. like-
All of this, I almost said shit. I didn't want to cuss. So I'll say crap instead. So all of this comes here and that gets pasted right there. And that's our answer.
Okay. So that would be the raw derivative?
Yeah, this would be a mess to try and clean up because you would literally have to distribute this through to every single one of those.
So if we like had a question like this on our exam, this would be like a okay answer to just leave it like.
Yes, this right here is the form that I would want to see right here. Just don't forget you have to multiply both sides by y, and don't forget to replace y with what it was in the very beginning.
Okay.
This technique that I just used, where we did natural log on both sides, has a name, okay? It's called logarithmic differentiation. That's what it's called. You're basically taking log on both sides to make it, turn it into something you can do and differentiate. Now, remember, I started this problem with Justin, and Justin and I agreed in the very beginning that we could have done quotient rule, but it would have been bad, right? But you could have. And so you might be saying to yourself, well, I don't want to have to do all this because I'll just go with the quotient rule. I'll stick with that and avoid all of this. Well, the bad news is that I can give you a problem where you have no choice but to use the logarithmic differentiation. So I'm not ready for that yet. I will do that. I don't want us to lose sight of something here. So let me take this over here for a minute. I don't want us to lose sight of what we ultimately have the ability to do now, or like what we just did. I'm going to take that very ugly function and I'm going to type it into Desmos and graph it. It's going to have a ton of asymptotes. There we go. Okay, so this is the graph of that function. Where is it? There's not much to it, huh? I don't see a lot there. Oh, because we have a square root. Yeah, we have a, sorry, yeah, we have a, wait, is that right? Yeah. We have a square root in there, so we can't have certain numbers or else it'll be undefined. So this is the graph of that very strange function. And if I wanted to know what the slope of the tangent line was at, let's say, 10, right? If I want to know what the slope of that tangent line was, then all I would have to do is replace all of these x's with 10s. And whatever that number is, would give me the slope of that tangent line, okay? So I promised this in the very beginning when we were learning about the derivative. I said the derivative is the slope of the tangent line. Here's the limit definition. We had to crank out limits to get derivatives and it sucked. Then we gave you the power rule, product rule, quotient rule, chain rule. We learned implicit differentiation. And now we have this logarithmic differentiation, which helps us even more. And all it allows us to do is do more and more complicated functions, right? Because in the real world, things are not as simple as y equals x squared. Everything's a lot more complicated. Okay. So let me give you another one of these. Yeah, let's try this. There we go. I'll give you some time. How about that? I want you to find y prime. And I would like for you to use logarithmic differentiation. All right, I'd like for you to use the technique that we just used. Don't try and do quotient rule. And I mean, if you're like totally adamant that I'm going to do quotient rule no matter what, then I'll just give you something that you'll just surrender to. All right, like you'll just be like, forget it. I can just make it more and more complicated. The log allows us to split everything apart and make everything doable, right? Like we never needed anything complicated to do this derivative, right? No quotient rules, no product rules, no, a little bit of chain rule. We did have to pay attention to the insides of these, but otherwise we didn't. You know what? I want to change one thing on here. sorry, I'm gonna change one thing. This x plus 4 on the bottom, I want you to make it 4 minus x instead. Got that? All right, let's take, I don't know, 8 minutes or so, 8 to 10 minutes, to see how you do on your own. I'm gonna put up a poll. When you're done, when you get a final answer, click yes, okay? That way I kind of know where people are. Enjoy. I'm gonna start working it out. We've got 3 people done right now. Okay, I've got the answer up there. I did skip a little bit of work from here to here. I did skip. I just did it in my head, but we can talk about it if you're not getting it. Let's take another minute. All right, what do y'all think? Don't have any questions? Take log on both sides. The way I think about it is everything that's in the numerator is going to be separated with pluses, and every one of them will have a log. So I just do log of that, log of that, log of that. And then everything in the denominator is going to wind up having a minus in front of it because of the subtraction. So I'm going to put a minus in front of the log of this one, and then minus in front of the log of that one. How about this? Can somebody tell me why this just became x squared?
Because the ln, like ln times e cancels out to equal.
Yeah, ln's the inverse of e.
Yeah, they're inverse. Now, that's correct, Bree, but I'm just going to correct the way you said it. You said ln times e. It's actually ln of e because it's composition. It's not multiplication. So the natural log of e to something, the e and the natural log go away. So we just got the x squared.
I thought that was Naja that answered that. Was it, Bree?
Was it Naja?
I think so.
Yeah, it was me.
No, it was
I'm sorry, Naja. I saw Bree unmute, and
Yeah.
then I looked down and didn't see who said it. Sorry about that.
It's okay.
Okay. And let's see. So then I pulled the powers out here. Power. And then I started taking the derivative. Left side, 1 over y prime. By the way, 1 over y prime is always what you'll get on the left side. Every time you do logarithmic differentiation, you're always going to get 1 over y prime. And then derivative of x squared is 2x. And then here, derivative natural log of something is 1 over it times derivative of what's inside, which is cosine. Here, 3 comes for the ride. Derivative of natural log of something is 1 over it times derivative of what's inside, which is just 1. -4 comes for the ride. This is a tricky one because of this -1. Derivative of natural log of this is 1 over it, but then the derivative of what's inside is -1. So I did that on purpose to try and trip you up. Derivative 4 is 0, derivative negative x -1. So you do get a -1 here. On all the others, you don't. You just get ones. So I don't put them. Sorry, this one. And then this one's just minus this. And then after that, I just cleaned it up. Cosine over sine is cotangent. 3 went on top. The -4 went on top with the -1, became a plus. And then I have to multiply both sides by y. Go good? Questions?
Where did you get the -1 from?
Okay.
Like the highlighted one?
Okay, yeah. So look at this right here. Just look at this part because the -4 comes for the ride. So if I want to take the derivative of the natural log of a box, it's going to be 1 over the box times the derivative of what's inside. So when we do 4 minus x here, the 4 minus x goes here, right? 1 over 4 minus x. But then we have to take the derivative of 4 minus x. And the derivative of 4 is 0. And the derivative of -x is -1. It's
Okay,
that right
thank
there.
you.
0 minus 1 is -1. So that goes here. That makes sense, Marissa?
Yes, thank you.
Okay. Okay, we're supposed to take a break in about 13 minutes. I want to show you one more problem before we do that. Y equals X. You know what? Let's do this one instead, because I want to be able to graph it. Let's do sine X raised to the cosine X. Find Y prime. All right. I'm going to go graph it, and then we're going to talk about it. Y equals sine of X raised to the cosine of X. There it is. There's the graph. Okay. Interesting looking graph.
Question.
Now, I can pretty much guarantee that in all of your algebra pre-cal classes, everything you've done in the past, you've never encountered a function like this. There's something uniquely different about this function. And what makes it uniquely different is that you have x's that are appearing within the base of the function and within the exponent. So like, yes, I realize that you've seen problems like this. Y equals, let's say, e to the x squared sine x. Okay, yeah, you've seen something like this because, or what we have here is the base is a number, right? And in the exponent, that's where your x's are, right? Your x's are up here. So we can handle this. If we have a number raised to something with x's, we can take the derivative. If you flip it around, you know, and you do something like x squared sine x, and you raise that to, let's say, the third power. Here, your x's are within the base of the function, and then the number is up here. You've never encountered a function where x's appear both within the base and within the exponent. And so taking the derivative, you cannot use the power rule. You can't use the power rule. You are not allowed to take this and bring it out front to take the derivative, because this right here is not a number, okay? It's not a number. If that were like sine x to the fourth power, then we could bring the 4 out and make it a 3. But we can't, okay? Because it's not a number. Was there a question?
Yeah, so I'm just gonna take a guess based off like the formula you showed us earlier. So would it just be sine of x to the cosine of x times ln sine x times the derivative of cosine of x negative sine x?
Yeah, so what you're looking at, what Cody's suggesting is, wait a minute, we have something, if we have a to a box, right? And we want to take its derivative, then we can do a to the box, natural log of a times the derivative of the box, right? That's what you're suggesting, Cody.
Yes, sir.
There's a problem with that. This formula only works if a is what?
Oh, if a is
A constant.
a constant, yeah.
Constant.
Okay,
And see, a here is not a constant. It depends on x.
okay.
So you can't look at this from the power rule perspective, and you can't look at it from the exponential perspective. Do y'all see that?
Mm-hmm.
Maybe we should wait on that problem. Maybe I should give you another one. How about this one? This will be much easier. X to the x. Okay, let's do that. We'll start with that one. If we take x to the x, graph it, there it is. That's x raised to the x. All right. That's the graph. It definitely has tangent lines, right? Somewhere on it, we can find tangent lines, slopes. So the derivative does exist, but how do we find it? So Cody, going back to what you're saying, we can't look at this using the rule x to the n and then just do n x to the n minus 1. We can't do that because this rule says that x is the variable and n is a number. So we can't do that because the n is not a number. And we can't do a to the x and take derivative of that, which is this. Can't do that because this says x is in the exponent and the base is a number. So it's neither one of these. It's uniquely different than anything we've done. But you can do it with logarithmic differentiation. So let's do it. What I'm going to do is take the natural log on both sides. Okay. And then on the right side, I am going to use the property of logs, which allows me to drop this out in front. That's a log property. I'm not doing power rule or any derivatives. I haven't taken any derivatives yet. At this point, I can differentiate though. So I like to put a little squiggly line. That just represents the fact that I'm about to take derivative. So I take derivative of the left, 1 over y, y prime. And on the right, how do you take derivative of x times natural log of x?
ln x plus ln.
Yeah, so product rule, right? You're just gonna do product rule over there. So derivative of x is 1 times ln x plus, what's the derivative of ln x?
1 over
x.
1 over x times
x.
what's the product rule? X, right? So we have 1 over y times y prime equals ln x plus 1. And there is one more step. Those x's canceled, right? You just got left with a 1 over there.
Right, then you gotta take your multiply by your original y.
Multiply by y. So I take this whole thing and I multiply by y, and y is x to the x. So the derivative of x to the x is natural log of x plus 1 times that quantity times x to the x.
So then in the problem of before, we can't use the power rule, but if we apply natural log to both sides, then we can pull that cosine of x into the front.
That's right. So on this one, if we do log on both sides, we pull the cosine out, and then we can do a product rule.
Okay.
Right. Let's do something here. We're gonna take a break, but I'd like to give you this problem. I'm gonna change the problem a little bit. Okay. Let me go back to the graph. I just want to double check something on it. I'm going to have to make it slightly different problem. Okay, so I'm just going to make up a problem real quick. All right, the problem I'm going to make up is going to be tangent x raised to the x squared. No, not what I'm looking for. Hold on. Oops. Give me a second. I got to make this work. Let's just do this. X squared. There we go. That looks fun. All right. Find equation of line tangent to y equals x. Hold on, give me a moment. I don't know if I'm having second thoughts on this one.
So say, isn't it gonna be really hard unless you've got the right values?
No, it's all right. To x squared plus 1 to the sine x at 0, 1. All right, so we are going to take our break, and then I'm going to give you time to try and work this out. So let's say that we will reconvene in about 15, let's go 18 minutes. So that's at 250. And at that time, hopefully you will have started this or worked some of it or whatever. But we'll come back at 250 and we'll figure out what the answer is here, okay? All right, did anybody get it? Anybody have the equation?
I got something, but I don't know if it's right.
Yeah, so like after you find the like, you know, you do like the differentiate like logarithmic differentiation, do you then plug in like the 0 and stuff to get like the
For
y?
X, right? You can plug in the 0 for X to get to figure out what Y prime is.
Which would be m, right?
That will be your M.
Oh, you X. I don't know why I plugged in the Y after I differentiated.
So maybe we should talk about the derivative.
Yes.
So here's the work. Oh, okay. So first thing you do is you take natural log on both sides,
Mm-hmm.
right?
Yep. Then you get product rule.
And then once you do the natural log on both sides, you pull the sine X down in front using property of logs. And at that point, you differentiate. And we will have a product rule right there. So derivative of left side is 1 over y prime. Derivative of right side is derivative of sine, which is cosine, times the second one. Plus, now the derivative of natural log of x squared plus 1 is a little tricky because you'll have 1 over x squared plus 1, but then times the derivative of what's inside, that's chain rule. And that's where the 2x comes from. And then you have to finish off the product rule, multiply times sine x.
I forgot the chain rule with the 2x.
Yeah, be careful, because if this is like x plus 1, then it won't matter because this would be 1, but because it's x squared plus 1, you'll have 2x there.
Gotcha.
Does anyone have a question on where the derivative came from or anything with the derivative? Next thing I did was multiply both sides by y. So I got rid of the y here, and then I multiplied this whole thing by y. So here's y right here. That's the original equation. And then here I didn't really do much. I just put the 2x sine x on top of the x squared plus 1. And so to find the slope of the tangent line at this point really means that I need to know what the x value is. So x is 0, so I plug in 0 into that derivative for x. So I get cosine of 0, natural log of 1 plus, when you put 0 here on top, you get 0. And on the bottom, you get 1. Then over here, you get a 1, then raised to the sine of 0 is 0, so you get 1 to the 0. Cosine of 0 is 1, but natural log of 1 is 0. So these two multiply to be 0. And 0 over 1 is 0. And 1 to the 0 is 1. And so when you multiply all that, you get 0. So your slope is 0. And so when you plug it into the formula, remember that's the formula y minus y1 equals m times x minus x1. That's what this is. Y1 is 1, x1 is 0, and the slope was 0. So you wind up just getting y equals 1, which is the equation of a line. I mean, it is. It's not a very fancy one, but it is. So here's what we're looking at. Here was the graph. We wanted to know what was the equation of the tangent line at 0, 1. That's 0, 1 right there. And you can see, I hope that's obvious, that, I'm sorry, the equation of that tangent line is just y equals 0. I mean, y equals 1. Okay. All right, I have another one. This is interesting. I'm not going to have you work on this one. I'm going to work it for you. It's another find the equation of a tangent line to some curve. We have a very interesting curve here because notice that this curve or this equation is not solved for y, right? That is not solved for y. And it won't be easy to solve that for y. So we're going to have to use implicit differentiation, not logarithmic, implicit, okay? To start off, we know we need implicit, which means I need to take the derivative on the left and right with respect to x. However, I run into a problem right away that I can't take the derivative of x to the y because both the base and the exponent both are things I don't know. They're both variables. So I can't use the power rule, and I can't treat it like an exponential. This is what Cody and I were talking about earlier, right? It's neither one of those. Same with the right side, y to the x, you have variables in both places. So we are going to do logarithmic differentiation now. We're going to take the log on both sides. Okay, so take the log on the left and take the log on the right. That allows me to pop the y out in front of the natural log of x, and on the right, it allows me to pop the x out in front of the natural log of y. Questions on that? Does everyone understand why the derivative of this is not yx to the y minus 1, right? That you cannot use the power rule. And also it's not equal to x to the y natural log x. That would be using the exponential rule for a to the x. Can't do it. But if I do natural log on both sides, then I create these two little cute little products, and now I can do implicit differentiation. So I can take the derivative with respect to x on the left and the derivative with respect to x on the right. And this is going to be a little tricky. Any questions up to here though?
No, then you just run product rule on both sides, right?
Product rule here, product rule here. Okay, let's carefully do this. Let's see, I haven't called on some people here. How about Brian? You there? Are you back?
I am. Sorry, I'm eating. I was eating. We're good.
Okay.
That's why I did try. I can still do it. We're good.
You good? Okay.
Yeah.
All right. So Brian, on the left-hand side, I need you to take the derivative with respect to x of this product. So that will be what?
It'll be. Hold on. So it would just be the product rule. So it'd be y or dy over dx.
dy dx. I'm going to write dy dx because that's what you said. That is correct. But let's just remember that that really is going to represent y prime. Okay.
Mm-hmm. Yeah.
Okay. Keep going.
Times ln x.
Good.
Plus. It's just. Shoot. It's 1 over x, right?
1 over x.
And then times y.
There you go. That's it. So Brian took the derivative of y with respect to x, dy dx, times the second function. Plus, now when Brian took the derivative of natural log of x, all he said was 1 over x. And that's correct. Because we're differentiating with respect to x, if you were to do the chain rule, after you do the 1 over x, go take the derivative of x, you will get a 1 because you're differentiating with respect to x. So there really is, if you really need to have it, there really is a times 1 right there next to this. And then to finish off the product rule, you multiply it times the first function, which was y. You want to keep going? I can come back, or I can, if you're eating, I can.
Oh, that's fine.
Good. You want to try the right side?
Hmm.
Okay.
So you would do it. It would just be 1 because of the.
Derivative of x.
Yep. And then that one times L, the natural log of y.
Okay.
Plus 1 over y.
Careful here.
And then the dy over dx.
Perfect. Okay, good. Does everyone see what happened there? Derivative of natural log of y with respect to x is 1 over y, but then the derivative of y with respect to x is not 1, it's dy dx. Good. Are we done?
No.
Oh.
You got to times x.
There you go. Good job. All right, so I'm just going to rewrite this so it looks a little different. We have y prime times natural log x plus y over x equals natural log y plus x over y times y prime. So here I just replaced dy dx with y prime, natural log x plus, here I put these together to slap the y on top of the x. 1 times natural log y is natural log y. And then here I put the x on top of the y and just slap the y prime next to it. Okay. Now we want to know what y prime is where. We want
At when x is 4.
at well, yes, at x is 4, right? But look at our equation. Our equation has x's and y's in it, doesn't it?
Mhm.
So I'm actually going to be looking at 4, 2. I'm going to have to replace all my x's with 4s and my y's with 2s. So what would it become? I'll have y prime, which I don't know the answer yet. Y prime times, okay, natural log of x. That's natural log of 4. Plus, what's y divided by x?
Be a half, 2
A
over
half,
4.
2 over 4. Okay, equals now natural log of y, which is natural log of 2. And then plus
2.
x over y, which is 4 over 2 times y prime. I need to know what y prime is. So it looks like I'm going to have to solve for y prime. Let me clean it up a little bit more. So made that a 1/2, 4 over 2 is 2. I'm going to put my y primes on one side. Everything that's not y prime, I'm taking it to the other side. So I brought this 2y prime to the left. I took the 1/2 to the right. And notice that this natural log of 4 is attached to the y prime. So I can't do anything with that. I can't move it to the other side. But what can I do here? The whole purpose of getting the y primes on one side is to do what?
You can factor it out.
Factor it out. If I factor out a y prime, I get natural log of 4 minus 2 equals natural log of 2 minus 1/2. Now I can divide both sides by
ln 4 minus 2.
4 minus 2. Now that's a number, right? I could get that as a decimal, but I'm just going to leave it like that. The equation of the tangent line is y minus y1 equals m times x minus x1. We know y1, right? y1 was 2. We know the slope. The slope is natural log 2 minus 1/2 over natural log 4 minus 2. All of that times x minus 4. Right? X was 4, y was 2, and this was my slope. Questions?
You would take that on like a test. You wouldn't want us to
Sure.
actually run the ln 2 minus that whole thing.
If you
could
give me
get a
the
number.
decimal, I'd be okay with that too.
Okay.
I left it like this because that's the exact answer. There's no rounding. What I'm going to do now is I'm going to go and verify this with the picture. So I'm going to go graph. I'm going to go ask the computer to graph x to the y equals y to the x, which I had already done before. There's the graph. Okay, here's the graph. Let me put the point, what was it? 4, 2?
Yeah, it was 4, 2.
Okay, so there it is. We want to know what's the equation of that tangent line right there, right? We found that it was y minus 2 equals, then it was like natural log of
2 minus 1/2 over
2 minus 0.5
Can you hear me?
over natural log of 4
Can anybody hear me?
minus 2. I hear you.
Yeah.
Okay, I was reading it out, then it sounded like you were just still reading it off, so I was confused, but it's okay.
And then x minus 4.
Mm-hmm.
Is it going to land on top of that dot, you think?
It should if we did it right.
There we go. We got it. That looks tangent to me. I think we have it. That was cool. All right, any questions on that? Okay, so that's logarithmic differentiation, all right? I think when you're on taking the test, the things you have to pay attention to are like for a problem like this, is this going to be obvious to you to do logarithmic differentiation or not, right? Like this one also, is it just, are you going to see it and go, logarithmic differentiation? Or are you going to be like quotient rule, I'm just going to grind it out? That's what you're going to have to kind of get to a point where you see it, right? That's logarithmic. When you get to a problem like this, well, then there you better see it because you've got x's in both the base and exponent. So you better see that that's logarithmic differentiation. And this one, same thing. And then this one was weird because you can't, it's logarithmic differentiation, but you have to do the logarithmic here first, and then after the rule, then you're doing implicit. So this is kind of a weird scenario. All right, I think we are good for this. I think you can now go and do the homework for 3-3. Remember I said don't worry about the homework for 3-1 and 3-2. I think you're good for 3-3. Yeah.
Hey, sir.
Yes.
Hey, I wanted to see real quick, since you said that there was only, like with the quotient rule, if we wanted to grind it out and you're all like, no, I can make you surrender by using the other logarithmic one.
Yeah.
Can we always use the logarithmic approach and always get it right? Or is there some where we have to use the quotient rule?
Well, okay, so like, for example, if I were to give you a problem like this. Right, like this. Could you use logarithmic differentiation? Yes. Now, it might be faster to just do quotient rule.
Oh, okay.
Okay, it might, because it's not that complicated. The top, right, the F here, that's F, and this is G. Is it hard to take the derivative of F?
No, yeah.
Is the
In
derivative
this case,
of G
it's
that
not.
bad? It's a product rule, no big deal. I mean, that's not too tough, right? But if I did something like this, where it was like, you know, x squared plus 1 sine x, and then like x minus 4 to the third over, and then, you know what I mean? Like I could just I could make this ugly to the point that you would.
So,
But I guess what I'm trying to say is like, just in case if we can't figure it out, if we should use one or the other, just in case, can we just go straight with the log form and we'll be all right?
You should, as long as you apply the derivative of the log correctly, you should be okay.
Okay. All right.
Yeah.
so then, I don't know, I'm noticing a pattern where it seems like if you have anything more than a double product on the numerator and the bottom, it seems like it's just better to go for the logarithmic differentiation.
Yeah, that's the real kind of tip, is that if you have got more than one product up here or down here, like you probably don't want to take the derivative of that. Could you? Yes, but it's going to be it's a double product rule. So that's going to be complicated. And then when you get to the bottom, it's going to be the same thing.
So if there's more room for error, it's safer to go with the logarithmic form then, right?
I would think so. I would think the logarithmic is going to be a little bit safer. As long as you use the properties correctly, it should be safer. The derivatives should be a little easier to do.
All right.
But technically you should get the right answer. I mean, the same answer. Like, look, Where's the problem we did? Let me look at this problem here. Okay, so we got this answer, right? Here's our answer. This is our answer. If I had used the quotient rule, okay, if I had used the quotient rule, here's what I would have gotten. Now give me a second. I just have to kind of grind this out. So the derivative, I do derivative of top first, which would be e to the x squared. Oh, sorry. Yeah, e to the x squared times 2x. That's a derivative of this piece. Then times the other piece, sine x times x plus 2 cubed. Okay, that's a derivative of this times that, plus now the derivative of this, which is another product rule. So I'd have to do cosine x times x plus 2 cubed plus 3x plus 2 squared times cosine x. That's the derivative of this piece, then times e to the x squared. But then minus, now do the derivative of the bottom, which is another product rule. Okay, do I really want to go through this? 4 minus x, I'm going to run out of room, times -1 times x to the 8th minus 8x to the 7th times 4 minus x to the 4th. That's a derivative of the bottom, but then times the top. So now I've got to put all of that here, and then the whole thing is divided by the bottom squared. So it's going to be very ugly, and it's not even going to look like this. They won't even look the same. They are the same, but they won't look the same. So I think there's a lot of room for error here. In fact, I hope I did it right. I mean, I was going very fast. So, okay. So what's next?
Just a question.
Yes.
My mic was muted. Just on the top when you were doing it, I don't think you actually put you did F prime. I don't think you did times G before you went on to G prime.
Yeah, that's what I'm saying. I went real quick.
Okay.
This was, well, it depends. I could split it like this. And so I'm calling like this is F and this is G. So F prime is this times G, which is this, plus G prime, which is derivative of that, which is its own product rule right there, times F. Then minus, I think I did it right.
But then aren't you supposed to, after you do all that, multiply that whole thing by the bottom, which is your actual G of the difference quotient?
Wait, hold on.
You do all that and then multiply that by the 4 minus x to the 4th times x.
Oh, yeah. You're saying this needs to be right there.
Yeah.
Yeah, that's there.
Okay.
Yeah, I ran out of room, so I gave up.
All right, I just was making sure I'm following
good,
the process.
Cody. Good. That right there should just steer you away, right? The fact that that's that complicated should just steer you away from it. Even though this isn't pretty, it's still a lot more, I think it's a clearer path to the answer. Okay, the next thing we're going to do is going to be very brief, okay? Remember in pre-cal that in pre-cal you were given the 6 trig functions, sine x, cosine x, tangent x, and then there's 3 more, right? Let me just put them here. We've got cosecant x, secant x, cotangent x, right? We have the 6 trig functions from pre-cal. We have already learned in this class what the derivatives of each of these are. The first 3 you should have memorized by now. Derivative sines, cosine, derivative cosines, negative sine, derivative tangent, secant squared, okay? The other 3, you know where to go to get the formulas for those, right? In case you need them, they're in your formula sheet, and they are right here, okay? Here are the derivatives of the trig functions. So what I'd like to do now is remind you that in pre-cal, after you learn the 6 trig functions, later on, you learn that each of those trig functions has an inverse function. So like for sine, there is an inverse of sine, which is written y equals sine inverse of x, right? And you're told, okay, you know, there's also an inverse for cosine. I'm not talking about derivatives. I'm just talking about the sine function had an inverse function. The cosine function had an inverse function. And each of these had an inverse, right? Every single one. Now, there are domain restrictions on inverse trig functions, which I'm not going to get into. You have to go back and review pre-cal. If you go back to the, let me see, where is it? Here it is. In the formula sheet, reference page 3, they talk about the inverse trig functions
This
and
is like,
domain restrictions on those. I'm not going to get into that. All right. You just need to be aware that they exist. All right.
question. Just the inverse is just basically like you put an angle into a regular and it gives you a value. You put a number or something like that into an inverse and it would give you the angle of where it's that value, right?
Yes, they undo each other basically. Now there's some little things you have to be careful with, but like just basically speaking, yeah, they just like E and natural log undo each other. That's what the sine and sine inverse do. So this class is about derivatives, right? So one thing I would be interested in knowing is, well, then what's the derivative of that function, right? Because you can graph that function if you want to. If you wanted to, you come over here and you could ask this to graph the arcsine function. First, I'll have it graph sine x. There's the sine function. Let's graph arcsine. See what it does there. There's the arcsine function. Now, it stops because there are domain restrictions, but that purple is the arcsine. And so I think it's clear that it should have slopes of tangent lines, right, on it. We should be able to find slopes of tangent lines. So, you know, what are they? What are the derivatives of these? That's the question. So let's start with the first one. Y equals sine x, or y equals inverse sine of x. And the question is for us to find y prime. Okay, so what is the derivative of that function? Well, you don't know, right? You don't know what it is. And do you remember how I showed you do you remember how I showed you that the derivative of sine was cosine? Do you remember how I did that? We'd have to go back and geez, I don't even know where it would be. Yeah, coming to it. Here we go. There it is right there. I proved to you that the derivative of sine of x was cosine of x, and I used the good old-fashioned limit definition of the derivative. I used a double angle identity from pre-cal, and I was able to convince you that the derivative of sine was cosine. And then the others I just skipped. I said, just trust me there that you can find them, okay? So if I want to show you that what the derivative of this is, I could try and use a limit, but it's not going to be nice. So watch what I do. This is going to be pretty cool. I'm going to take sine on both sides. Now, what I'm showing you right now is a proof. You don't need to actually know the proof. You just need to know at the end of the day what our answer is, okay? That's the part you're going to need to know. But I want to show you how we get it. So I take sine on both sides of the equation, and on the right-hand side of the equation, I just get x. And that's because when you put sine and sine inverse together, as long as the domain restrictions are met, you can cancel these out and just get x. So there's a little asterisk here about domain, but again, I'm not going to get into the domain restrictions. And now what I'm going to do is I'm going to take the derivative on both sides of the equation with respect to x. In other words, I'm going to do implicit differentiation. And let's see, Roger, you know, I don't think there's a Roger here. How about Christian? Christian, you there?
Yeah, I am.
Okay, so Christian, what is the derivative with respect to x of sine of y?
It would be cosine y times dy dx.
Times dy dx. Chain rule, everyone, right? The derivative of y with respect to x is dy dx. Christian, what's the derivative of the right side?
1.
1. Because the derivative with respect to x of x is just 1. And this guy is really y prime, right? That's what we're looking for. So what we have is cosine of y times y prime equals 1. So Christian, we're almost there. What's y prime according to what we have here? If I ask you to solve for y prime, what can you do to
1
get y
over
prime by itself?
cosine y.
Divide both sides by cosine of y.
Yeah. So
the answer is 1 over cosine y, right? But there's a little bit of a problem with this, just a slight little problem. That is correct, but our original function, y equals inverse sine of x, right? Inverse sine of x. Our answer, y prime, doesn't have x in it, right? It has y in it, not x. Go with me? I would like to see if maybe we could rewrite this so that it has x's in it, not y's. Okay? Are ready for this? I'm about to show you something that you're going to use a lot in Cal 2, all right? We're about to create what's called a reference triangle. You did this in pre-cal, but you didn't know why. Okay, so I would like to know what 1 over cosine y is, but I want it in terms of x. So I'm going to go back to this original equation right here, right there. See that? Sine y equals x. And I'm going to draw a reference triangle. And what the hell is a reference triangle? Well, it's just a right triangle that you draw that visually represents this equation. Sine of y equals x. So sine of y equals x implies that y is an angle, right? Y is an angle. So I'm going to put the angle y into this triangle right here. Now, sine, by definition, sine is which side over which side?
Opposite over hypotenuse.
Opposite over hypotenuse, right? That's what sine is. So if I look at the right side of this equation here, x, I'm going to rewrite that as x over 1, right? Because I can always rewrite x as a fraction. And that would mean that the x, I could look at that as being the opposite side, and the 1 could be the hypotenuse. So I'm going to label my triangle x here and 1 here. So do you all agree at this point that this triangle is just a visual representation of our original equation here? All it is a visualization of that equation. Good? Now, what are we interested in? What is our final answer? We are looking at 1 over cosine of y. Wait, hold on. What, isn't that secant y? That's also secant y. I can write it that way. The reciprocal of cosine is secant y. So let's see here. Wait a minute, hold on. This triangle has y in it, doesn't it? Like it has y. So if I want to know anything about cosine of y or secant of y, which side of the triangle am I going to need? Cosine has to do with which side?
The adjacent, so you're gonna need the
Adjacent
bottom.
and hypotenuse, right? I don't have the adjacent, do I?
So you could say,
But could I get it? Could you find the adjacent?
Yes.
Yes, let's call the adjacent, let's call it A. We know the Pythagorean identity tells us that a squared plus x squared must equal 1 squared, right? A squared plus x squared is 1 squared. And if I solve this for A, square the 1, subtract x squared on both sides, take the square root on both sides. And I'm only going to use the plus on the square root, not plus or minus. I'm only going to use a plus because A represents the length of a side of a triangle here. So there's A. So I know that this side is the square root of 1 minus x squared. And that means if I wanted to know what cosine of y was, right, that's what I wanted. Well, I want 1 over it, but let's just figure out what cosine of y is. What's cosine of y according to this?
1 minus x squared, or square root of 1 minus x squared over 1.
Yeah, square root of 1 minus x squared over 1. It's just adjacent over hypotenuse. That's what cosine is by definition. And so that's just square root of 1 minus x squared. And so back over here, if I wanted to know, forget the secant, we'll just do this. What's 1 over cosine of y? Well, that's 1 over cosine of y, which we just said is square root of 1 minus x squared. And there it is. That's what y prime is.
So we just have to like memorize those, or is
You
that
know,
like,
you do not need to know, like memorize how to do this, but I am going to just forewarn you that in Cal 2, this whole idea of a reference triangle is used a lot.
Would we not rationalize that then, or we could just leave it like that?
No, just leave it like that. You don't need to rationalize it.
Okay.
No. Let me see if I can convince you of this. Let me go real quick to my YouTube channel. How many we got? We got another hour.
Speaking of which, I do really enjoy that feature of the class, all the YouTube videos and everything. It really helps.
Good. I
Just
hate
throwing
the
that out
video.
there.
I hate the
yeah,
damn,
that's like the best.
ads that are here now, but let me
Yeah.
see.
Ad block's amazing, sir. Ad block is amazing.
How do you get ad block?
Yeah, if you have like Chrome or something, basically it's like a downloadable, like a widget or something like that you could use.
It'll block the YouTube ads?
Certain ones for, I mean, I
Oh.
don't know how much you get out of like Firefox or Edge and things like that, but I mean, with Google, you can get something that blocks pretty much everything.
If you have the ad block plus, then
Mhm.
it'll block all of like the ads, not even just on YouTube, but other websites as
Yeah,
well.
pretty much,
I'll
is-
have to
and
look
it's
at it.
free. You just want the
I'll-
one, it's
I'll
like
have
a,
to look into
a
that.
red, a red hexagon with AP or AP or something like that.
So this is a Cal 2 problem, or this is a Cal 2 class that I'm doing here. Let me just see here. Oh, there we go. Right there. So I'm working on a bigger problem, and then over here I've got a reference triangle. Do another problem here.
I will say it is.
Yep,
like
there
when
it
the-
is, another reference triangle.
When the videos are older, it throws me off when you don't have glasses in the recordings.
Well, I don't need glasses when I'm standing in front of a board.
Okay.
I only need glasses when I'm looking at a screen. Sucks, I hate it.
I need glasses if I'm trying to look at anything far away.
Okay, so I'm not sure I'm convincing you here or not. I'm trying to convince you. I've shown you a couple problems where we've needed it. Somewhere in here, I'm going to reference, there it is. Okay, there we go. Almost every problem in this section requires reference triangle. So although you don't need to be able to do a proof like this, I do want you to understand how you can use something like this information to create a triangle from it. And then once you have that, you can figure out, you could tell me from this what sine of y is, cosine of y, tangent of y, secant of y, cosecant of y, cotangent of y. You can tell me everything I need to know about y. Okay, so I could do the same thing for our cosine. So on your formula sheets, go to your derivatives. Zoom this in for you. You can see here, formula 19, inverse trig functions. The derivative with respect to x of arc sine of x is 1 over the square root of x, 1 over the square root of 1 minus x squared. The derivative of cosine of x, inverse of x, is negative 1 over the square root of 1 minus x squared. And then they continue, okay? Oh,
So
there's
there
more.
wasn't any tangent or cotangent there. So does that mean there's something wrong with those? Or
No,
actually, I
they're
didn't
here,
see 'em.
they're here. I just zoomed in too far.
Okay.
Yeah, there they are. So here's the 6 derivatives of the 6 inverse trig functions. All right, they're there. Please be aware of them. And I want everyone to take special note of this one. The inverse tangent's derivative being 1 over 1 plus x squared. Okay, I'm going to write it down in our notes, but this one right here, you take inverse tangent of x and you take its derivative, you will get 1 over 1 plus x squared. I want you to know that one because, again, in Cal 2, that becomes very useful to us. All right, so does everyone understand that since we've come back from our break, basically this new idea of you have your 6 inverse trig functions from pre-cal, and now I've just thrown these new 6 derivatives at you. Everyone understand that? So now I can basically ask you to take derivatives of these things with chain rule and product rule and all that other crap, built in like this. let's say that y is equal to, I don't know, x squared inverse sine of x. Find y prime. So what are you going to have to do? Gabriella, are you there?
Yes, sir. Wouldn't you do? I want to say product. but-
Product? You see the product here? Good.
Yes.
Okay, so let's crank it out. What do you got?
2x,
2x.
and then it's that 1 over the square root.
Do the product rule though. So that's a derivative of the first one. Then product rule says, so this is your f, this is your
Yeah.
g. So we're doing f
Yeah,
prime
the
g
prime.
plus g prime f, right?
Oh, so the inverse of sine x.
Yeah, there you go.
plus-
Plus now the derivative. So that was 1 over
The
the
square
square
root
root of 1 minus x squared times
x squared.
x squared. There it is. That is the derivative of x squared times arc sine of x. Questions? How about this one? Samuel, you there?
Yes.
All right, Samuel. What do you think? Let me go get the formula for you. How about that? I'll go grab them for you. Okay, so here are the derivatives of the inverse trig functions. So Samuel, when you look at that, y equals cosine inverse, and then you have square root of x. That square root of x is inside that inverse trig function, right? It's in there.
Mhm.
So you've got composition here, right? That's not multiplication. So try and see if you can do the chain rule here. What would the
Chain.
derivative of this be? Starting with the outer function.
So that would be, is that a negative?
Yeah, there's a negative here. I'm going to put the negative on top. I like to put the negative up here, not here.
Okay, -1 over square root of 1 minus x squared.
Okay, 1 minus, now be careful here. Everyone be careful here. What's the thing being plugged in? Square root of x, right?
Square root of x.
So you're going to be plugging that in for x and then squaring it.
So it'll just be x.
It'll just be x, but I'm going to put it in here just so everyone understands what we're doing. Okay, so the derivative of inverse cosine of something is -1 over the square root of 1 minus that something, squared. And that takes care of the cosine inverse. Are we done, Samuel?
No,
Okay, so what do we still need?
we still need the outside, multiplied by
Mhm.
the derivative of the inside.
Right?
Yes.
So what is the derivative of that? So what's the derivative of the square root of x?
It's 1/2 x and then -1/2
Yes.
on the power.
Yes, that works, but remember I told you every time you do square root of x, take its derivative, it's 1 over 2 root x. It's just a shortcut.
Mhm.
So now this becomes -1 over the square root of 1 minus, and I'm now going to change that square root of x to x, or square root of x squared to x. And then I have times 1 over 2 square roots of x. There you go. There's a derivative. Y'all good? How about this one? Try and do that. And then after you do that, try and do this. I'll give you a few minutes. On the poll, let me know when you're done with both of these. Probably only wait till about half of you are done. And of course, the instructions are to find the derivative. I didn't put it there.
Sir, I just had a basic question.
Yes, sir.
So like when I get 1 over tangent inverse of 4x, can I just turn that into cotangent inverse of 4x then?
No, because raising it to the -1 does not mean 1 over it.
Well, no, but I'm gonna take the ln of that, the derivative of that ln of tan x is 1 over tan inverse of 4x, isn't it? And then I turn that into the cotangent.
Okay,
inverse.
so you're saying when you take the derivative of this, you're getting 1 over, say what you got?
Yep, 1 over.
1 over what?
Tangent inverse of 4x, because isn't it supposed to be 1 over the?
Okay, tangent inverse of 4x.
Yes, sir.
Okay.
And then
you're going to keep going, right?
Right. I just was wondering if I could turn that.
So your question, this is a good question. Everyone pay attention to this. The question is that the same as cotangent? What, cotangent inverse?
Mm-hmm.
Or no, just cotangent? What are you asking?
I'm saying if I could turn that just into the cotangent inverse, because cotangent and tangent inverse are reciprocals.
So are they reciprocals is what you're asking? Right?
In this case, yes.
No, they are not. We have to be real careful. This -1 does not, I don't think this is what you mean, but this -1 does not mean tangent of 4x to the -1. This -1 represents the inverse. And this is one of the drawbacks to our notation, is that we use the same notation to mean two different things, so it's confusing. So just leave it as 1 over tangent inverse of 4x.
Okay.
We may as well work through this. We got at least enough of you done here. Okay, so we'll do the second one because we already started. The derivative of natural log of something is 1 over it times, okay, now who's up? Marissa's up. Marissa, you there?
I am.
Okay. Had you done the first one or do you want to?
I was still doing the first one.
Okay, well, let's
But
do the
I didn't
first
get that far, to be honest. I didn't know what I was doing.
Okay, so let's walk through it together. All right, so Marissa, we're taking derivative of e raised to something, right?
Mm-hmm.
Okay, what's the derivative of e raised to anything?
The same thing.
The same thing, right? Itself, right? So it's just going to be this. But now, Marissa, we have to use chain rule, so we have to multiply that times the derivative of what was up here. Okay? We need the derivative of this now. So Marissa, what is the derivative of the inverse tangent of something in yellow? So look at the box.
1 over 1 plus, is it 4 squared? Would it be 4 squared?
It would be 4x
Okay.
squared. Good. Does everyone see that? Because the argument of the inverse tangent function is 4x. The formula says whatever's here gets squared. So just like in the previous problem, when we had the square root in there, we have to square it. Same thing here. We have the 4x, we have to square it. Now, Marissa, we're not done. Chain rule says times, now you have to take derivative of what was in the inverse tangent function. And what's the derivative of what's in there?
4.
4. That's it. Now we could write this a little different. We could go 4 e to the inverse tangent of 4x over, you could change this into 1 plus 16x squared. Actually, you could actually square the 4x. 4x times 4x, 16x squared. And then just move the 4 up to the top and then make it join up with the e. That would be a pretty clean answer right there.
Okay.
That makes sense, Marissa?
Yes.
Okay, good. Cody, it happens to be you for
Alrighty.
the next one. So
I did the ln first, and then
Yeah.
you got to move into your chain rule on the inside. So it's going to be times 1 over 1 plus 4x squared, and then times the inside, which is 4 for the derivative. So it's on 4.
So same, it's almost the same thing that Marissa and I just did with the E, except that it's just that first piece is a little different.
Mhm.
Questions there? Okay, so look, everyone. Here's where we are. I have good news. In terms of derivatives, okay, if you look at the formula sheets, reference page 5, differentiation rules, these are all the rules we learn in Cal 1, right? And then this table of integrals is Cal 2 stuff. So in terms of this page, we have done all these rules. Chain rule, constant, subtraction, quotient rule, power rule, derivative of E, derivative of A, derivative of natural log, derivative of log base A, derivative of sine, cosine, tangent, cosecant, secant, cotangent. We've done all the inverse trig functions have derivatives. We now know they exist. And that's where we stop in Cal 1. There are still some more derivatives to learn, but you learn those at the beginning of Cal 2, all right? So we still have to learn about these things called hyperbolic functions. And we learn about them, and then we realize that each one of them has a derivative. So there are 6 new functions you have to learn, hyperbolic trig functions. And then each of those has a derivative. And then each of those hyperbolic functions has an inverse, and each of those inverses has a derivative. So there are still 12 more functions that you need to learn. And after you do that, you've basically got everything you need to progress through pretty much all the math that you'll probably ever do, unless you're, well, you'll learn other functions, but this will get you to where you need to go. All right. So for this class, we are done with me giving you functions to take derivatives of, and in the sense of there's not going to be any new functions I give you. Say, hey, we need to learn what the derivative of this is. We've got all the functions in our toolbox. We've got them all here now. All right. And now it's going to be time to go use this to do something practical with it. Okay.
So you're basically saying any problem that you give us from this point on, we should theoretically be able to figure it out.
You should be able to take the derivative of any function that I give you. There's no more, because like as of last class, you could only handle, well, as of last class, you could not do any of this, and you couldn't do any of that as of last class. As of now, you now can include those, and there's nothing new. There's nothing else that I'm going to give you. Okay? So that's good. We've kind of reached a terminal point in terms of derivatives. I'm debating what I want to do right now. I feel tempted to show you where we could have used an inverse function. So let's go back to last class. I'm going to show you this. So take a deep breath, see if you can remember this. We had a plane that was flying 2 miles high, 600 miles per hour. The plane was headed to a ground radar station. At a specific moment in time, we wanted to know how fast the angle for the radar station was changing. Remember that problem? At a specific instant. And what we did is we drew a picture of the exact instant. We drew a picture of the general situation. We figured out, what dr/dt was. That was the speed of the plane. And then we wanted d theta dt. And we had to come up with the relationship between r and theta. So we looked at this triangle and we used the 2 and the r, and we said that tangent theta would have to be 2 over r. Yes? You'll agree with that? I mean, that's what we did, right? At this point right here, when we had this equation, we differentiated it, right? We differentiated it. And when we differentiated it, we had secant squared theta, and then we had a d theta dt that came out from chain rule. And then over here, I had changed this a little bit to make it easier to differentiate with the power rule. So at the end of the day, we had this formula right here.
Could we have just arctanned both sides and then we cancel out and you get theta is equal to arctan of?
Yes, Cody, you're 1 step ahead of me. That's good though, you're seeing that. So when we got to this thing in a box, we actually knew it was easy for us to get r, right? R, we just used a little Pythagorean, we got square root of 32. The trouble, I guess the more complicated part was figuring out what theta was. We had to figure out what theta was because of this piece right here. We needed to know what theta was. Remember that? And so we had to go work on it. Instead of doing that, had we taken this equation right here, let me do it in green. Had we taken this equation, tangent theta equals, I'm still going to write it 2r to the -1 like that. if we had done that, well, you know, I'll write it as 2 over r. I'll leave it. 2 over r. If we had done this instead, and this is what Cody was just saying, if we had taken the inverse tangent on both sides right now, the left side becomes theta because they kill each other off, and the right side is the inverse tangent of 2 over r. Yeah, I'll do it, 2 over r. Now, you may be saying, okay, well, who cares? I mean, that doesn't really do anything for us, but watch. If we now take the derivative with respect to t, the left side becomes d theta dt, and the right side becomes whatever the derivative of tangent inverse of something is, which we actually know now, right? It's 1 over 1 plus whatever the argument is, which is 2 over r squared, right? That's the formula for the derivative of the inverse tangent, times, now I need the derivative, I need the derivative of this yellow piece. So that is where I will look at that as being 2r to the negative 1. I need to take the derivative of that, which will be negative 2r to the negative 2. So I'm just doing power rule, negative 1 comes out, r to subtract 1. Y'all all right with that? One more thing, dr dt. So if you follow that, what is the benefit of this versus this? Remember, we wanted to know d theta dt, and we had dr dt.
I was trying to have my mic was muted. We have what we're looking for in d theta over dt. We have dr over dt on one side by itself, so we can just basically plug and play at this point. We've got all the values.
Yeah, and r was easy to find, right?
Right, with Pythagorean.
So in this, if we do it this way, the only thing we need to know is r and dr dt. That's the only 2 things. But to do it the other way, we needed to know what theta was, we needed to know what r was, and dr dt. But it was the theta was the piece that was a little harder. So by just doing that inverse trig on both sides, we actually create a little easier problem for ourselves.
Okay, question.
Yes.
So for like when we go to the next test and there's implicit differentiation on there, will you specify where you want that method? Kind of like on the first test, there were spots where you wanted us to use the traditional limit method before we did like power rule and all that jazz.
Nope, you now can use anything.
Freedom.
Yep. You're free to use whatever. Okay, everyone, we've got about, what, 37 minutes or so. Y'all doing all right? No? So while Jesse, thank you for the honesty. So while we were sitting here, I got a text in the middle of class, in the middle of our class. It was from one of my Cal 2 students. And they said to me, hello, I'm currently doing some improper integrals and realizing that my skills with L'Hopital's rule aren't as good as they used to be. Can you point me in the direction of some of your lectures on the topic? So this is a Cal 2 student reaching out to me about a specific item that is covered in Cal 1 that he doesn't quite remember very well. And that is exactly what we happen to be doing right now. I'm about to start, okay? Well, let me just show you, okay? It's pretty awesome. This is a new section, by the way. This is 3.7. Okay, this is 3.7 in the book. Now, the way you say that, it's debatable. The way I was taught is L'Hopital's rule. L'Hopital. L'Hopital.
You're saying L'Hopital almost?
L'Hopital.
At first, when I first saw it, that said hospital, but
The hospitals, right? La
Hospital.
It's spelled La Hospitals, but it's L'Hopital. Now, there's actually some interesting history behind this rule. and I'm gonna have to go look this up again, but I believe that this rule, L'Hopital is this guy's last name, okay? So I believe, please, I'll correct myself if I'm wrong. I'll look at this up after class. But I believe that the person who actually came up with this rule is not L'Hopital. I think, if I remember correctly, that it's Euler that came up with it. I'm gonna have to check. It might have been Cauchy, but I think it's Euler. So you know how I'm trying to think of an analogy in the real world.
It
It's
was
like-
Johann Bernoulli, by the way, that actually did it.
Was it Bernoulli? Okay.
Yeah.
Okay, why? Well, I was way off on that. Why was I thinking Euler? So it's like Bernoulli, this guy L'Hopital like funded Bernoulli's research and gave him money to come up with stuff. And basically because he paid him to work, he got to put his name on it, something like that. I'll have to go look up the history of it. But so L'Hopital didn't do this, but he gets the credit. I guess he gets the name for it. All right, this L'Hopital's rule is completely awesome. All right, so what we have to do is we have to take just a step back, because if you look at the way this class started, what did we start with? What was the very first topic in this class? You don't remember? Limits, right? And then after we did limits for a while, and we suffered through them. After we did limits, we said, hey, there's this one specific limit that you do with a quotient, difference quotient, and that's this thing called a derivative, right? And then now here we are, and I'm actually going to ask us now to go back and do limits again. And I know that's going to make you not happy, but L'Hopital's rule, I think you're gonna like it. Okay, so L'Hopital's rule says this: if you're taking the limit as x goes to, it doesn't even matter what x is going to. So who cares what it's going to? Let's say you're taking a limit, and on top you have some function in a numerator, and on the bottom denominator you have some function g of x. So you're basically taking the limit of a ratio. And let's say that when you do this limit, you get something that looks like 0/0, or you get like positive or negative infinity over positive or negative infinity. Now remember, when we were doing limits, whenever we saw 0/0 or infinity over infinity, I always told you that that meant that it was what? I said, remember I said, anytime you see 0/0, that's bad, right? That's bad. We need to do some algebra. We need to do something, right? So we know that for any time we've seen this in the past, we've had to do algebraic work. L'Hopital's rule says that if you ever get this, okay, if you ever see 0/0 or infinity over infinity, if you ever see it, then if the limit exists, because it may not even exist, but if it exists, it is equal to the limit as x goes to whatever it is going to of f prime of x over g prime of x. So again, you're trying to figure out a limit and you're getting 0/0, or you're getting infinity over infinity, or negative infinity over negative infinity, or positive or negative. It doesn't matter on the infinities. If the top's getting huge and the bottom's getting huge, positive or negative, it doesn't matter. In either one of those cases, if the limit does exist, then it's equivalent to this limit, which is not this limit, right? It's a little different. What you're doing is you're taking the derivative of the top and the bottom. This is not the quotient rule. This is just derivative of top and bottom.
So we could just take them separately, just the top, and plate it up there, and then the bottom.
And then just take the new limit. So let me give you an example. Limit x approaches 2 of x squared minus 4 over x minus 2. Let's go back to the good old days, all right? If we're doing a limit, remember the first thing I ever told you, or I always told you to do on a limit is just plug in and see what happens, right? So we plug 2 into the top, we get 0. On the bottom, we get 0, right? So we would normally have to do some algebra here. And does anyone remember the algebra we would do for this one?
Good factor.
Yeah, you could just
Factor the top, difference of squares, and then things would cancel.
Mhm.
But L'Hopital's rule says that what we can do is this limit, if it exists, will be equal to a new limit that we can do. And the new limit that we do is the derivative of the top. What is the derivative of the top?
2x,
2x over the derivative of the bottom, which is
1.
1. And now take that limit. So let x go to 2, and what do you get here?
4/1.
You get 4/1, which is 4.
Which is
Now,
the
if you
same.
don't believe that that works, let's try it the way that we learned it before. We would have done, you said difference of squares on top.
Yeah, your x minus 2's would cancel.
The x minus 2's cancel, and then when you plug in 2, you get 2 plus 2, and you get 4. And that's not a coincidence. That is L'Hopital's rule. Now, one thing I have to point out here, do you see the step from here to here? What I did was I applied L'Hopital's rule, right? Like I actually used the rule. So normally what we like to do is we like to do something to let people know we used L'Hopital's rule. So instead of me just writing that this limit is equal to this, you usually put an H on top of the equal sign for the H in L'Hopital, or just something. I've always put an L. I don't know, that's just me. I've always put an L above it for L'Hopital, but a lot of people put the H. A lot of books use H. Doesn't matter. You should just somehow let someone know that you're not saying this is equal to this. You're saying by L'Hopital's rule, they're equal. What do y'all think, man? This is fantastic.
That's actually pretty neat.
Yeah, this is really cool. So let's do another one. Limit x goes to infinity of, how about this? 3x squared plus x plus 1 over, let's say, 4x squared plus 1.
Well, you run it, you're gonna get infinity over infinity right away.
Yeah, so we go and we do our normal thing, which is we just replace our x's with infinity. We can see that the top becomes infinitely big, the bottom becomes infinitely big. And does anyone remember how we deal with the infinity over infinity? There was something specific we did in this case.
Clear your x's, so 1/x squared.
Yeah, we
Clear
look at the
those.
highest power of x on the bottom. Remember, then we bring it in as in the top and bottom as 1/x squared. Not anymore. By L'Hopital's rule, this limit is equal to the derivative of the top, which is 6x plus 1, over the derivative of the bottom, which is 8x, right? And now you take the limit again. Uh-oh. What do we get?
Still infinity over infinity.
You still get infinity over infinity. Well, that didn't help. It's okay though, because L'Hopital's rule says that if this limit exists, right, that you can take derivative of top and bottom. So we can do L'Hopital again on that. And derivative of the top would be 6, and derivative of the bottom would be 8. And at this point, x isn't even here anymore, right? So your answer is just 6/8, or what, 3/4?
Right, and if we did the original method, it would have canceled all the x's, let them go to infinity, and you'd had 3/4.
You would have wound up with 3/4, yeah.
So we could technically use this rule for all of the other limits that we did at the beginning of this.
A lot of the limits that we did in the beginning, a lot of them can be done this way. Now L'Hopital's great, okay? I'm not gonna knock it at all, but there are some problems that as you start to do the derivative of top and bottom, it actually gets more complicated. And L'Hopital's rule doesn't work.
Yeah, I was gonna ask what a situation where like L'Hopital's rule would be, worse for us to do than the actual old limit method.
Would
Yeah.
it not work with a constant on the bottom? Or
Well, if you had a constant on the bottom, then you shouldn't have a problem. Like you shouldn't have anything bad,
oh, that's true.
right? Because your numerator would not, whatever the numerator does, the denominator's not causing a division by zero, so you should be okay. Do y'all remember that one? Remember I told you to
Yeah,
memorize?
it's one.
this stuff?
It's one.
One, right?
Sign
Just
of
the
junk
one.
over some
Sign
junk
of
is
junk
one.
over junk, that's one. Remember I told you just take it on faith? Okay, well, why is it that? Well, this is 0 over 0, right? So
Right.
we're allowed to use L'Hopital.
Cosine of x times 1 over 1, and then cosine of 0, if you let it x under 0 is 1, so 1 times 1
Okay.
over 1.
Derivative of top is cosine, derivative of bottom is 1. And now let x go to 0. Cosine of 0 is 1. 1 over 1 is 1. This is usually when students start getting mad at me. And they start saying, well, why didn't you show this to me from the very beginning, right? But do you understand why? There's a reason why.
The derivative.
You didn't know what a derivative was, right? So how am I supposed to tell you to take a limit and take the derivative of the top and bottom if you have never learned what a derivative is, right? Not only did you not know a derivative, this is the thing that can be really cool about math and just science in general. We started with this idea in this class of a limit, right? From that was born the idea of the derivative. Right? Limits are hard to do, right? But there's a specific type of limit that gives you a derivative. And it turns out that you can actually use those derivatives to come back and do limits, which is kind of fascinating. But I couldn't show it to you before, I apologize. All right, now you have it though. Now you've got it, it's in your toolbox. It's a huge tool, okay? It's a huge tool. But just like everything else in this class, as soon as I give you something that's good, what happens?
We escalate in difficulty.
Yeah, it just things get harder, right? So that's kind of what's going to happen now, is that things are going to get a little bit worse. Go ahead.
How would this rule work if, like, let's say we were to have to take the limit of something and the f of x has like a square root? You know how typically we would take the conjugate?
Yeah, I don't know. I mean, okay, so like, what if we want to do limit x goes, I'm just going to make this up on the fly, square root of x minus 2 over x minus 4. That's a limit that we would have seen in the past. Right? Is this what you're talking about? Something like this? Okay, so I hope it's clear to everyone that this gives us 0 over 0, right? So I'm going to go for L'Hopital. Okay, derivative of the top is 1 over 2 root x. That's the derivative of the top, right? Because derivative of the square root of x is 1 over 2 root x. Derivative of negative 2 is 0. So that's just the top. What's the derivative of the bottom?
1.
1. Oh, well, that's not bad. Plug in 4 for that. 1 over
4.
2 square root of 4, which is just 1 over 2 times 2, which is just 1/4. We're done. Let's move on. So no conjugates needed. It's beautiful, isn't it? I mean, it's just an awesome rule.
And you'd still get the same if you did the conjugates anyway, so.
Yeah. Okay, let's see if you remember this type of problem. I love putting these problems on tests. Limit theta goes to 0, at least like on the first test. Remember those on the first test where you would have to like split it all apart and then like figure out what you need to like put in to make the sine junk over junk happen? Remember all that? Like half the class doesn't understand what the hell's going on. The other half is like, you know what I'm saying? Like this is one of the harder problems. Maybe not anymore. We get 0 over 0. So here comes L'Hopital. L'Hopital. Okay, be careful. Derivative of the top.
It's going to be cosine of 3 theta times 3.
times 3. Don't forget the 3. The 3 comes from the chain rule, right? Because you have sine of something, take derivative, get cosine of it. Derivative of the inside is 3. Bottom,
So
the
see
tangent of 5 theta is secant
squared
squared 5 theta, but don't forget the
5.
times 5. And now you plug in 0. 3 times 0 is 0. Cosine of 0 is 1. So top's headed to 3. Secant of 0 is 1. Square that, you still have 1, and then multiply times 5, you get 5. 3/5. God, would have been nice to have this. Right?
Well, all I can say is we appreciate it much more now.
Yeah, yeah. Yeah, you have to kind of suffer a little bit to have a true appreciation for it. Let's see here. Let me just figure out what I want to do now. Okay. What are we doing on time? Okay, here we go. How about this one? Limit x approaches 0 of x, 0 from the right of x natural log x.
Has to be coming from the right just because you can't have negatives in your natural logs, right?
That's right. That's the only reason I put a plus on the 0 is because you can't have negatives. All right, so next the person up here is Matthew Diaz. Are you there, Matthew?
Yes, sir.
Okay, all right. So help me out here. Just kind of tell me what this looks like this limit is headed to. Like, where's each piece of this headed to?
And I mean, I don't know. The first thing I see is like maybe well, it's headed to 0.
Okay, this is headed to 0. I agree with that. But then it's being multiplied times this natural log of 0, but we're approaching 0 from the right. So do you remember what the natural log function does as you approach 0 from the right?
No, I don't remember.
No? Does that help?
Mm-hmm. Yes, sir.
Okay, so where is the natural log function headed as you approach 0 from the right?
To infinity.
Negative infinity.
Negative
Right?
infinity.
Negative infinity. So what we have here is 0 times negative infinity. Now, I should restate that. We have something that is approaching 0 times something that is approaching negative infinity, right? That does not equal 0, and that does not equal a negative infinity. That equals, shit, I don't know, is what that equals, okay? That means you don't know what it's doing. That is an indeterminate form. It's like they're battling each other, okay? And so we have to figure out what's going on. Now, Matthew, can we use L'Hopital for this?
Yes.
What did L'Hopital say? Let me bring it back up here. What did L'Hopital say? Look at the statement here. If you have a limit and you have this, is that what we have?
No.
No, we don't. We don't have 0 divided by 0, do we? We don't have infinity divided by infinity. You're not allowed to use L'Hopital's rule unless you see that, okay? And right now we don't see that, okay?
So it would just be a product.
So there's a quick fix for this, all right, Matthew and everybody. There's a quick way that we can fix this anytime we see this, okay? Anytime, I'm gonna say it again, anytime that we see 0 times infinity or 0 times negative infinity, anytime we see that, we can make it look like L'Hopital's by grabbing one of them and dropping it to the denominator. Now, let me show you first before I explain it more. I'm gonna rewrite the limit. Now, Matthew, I'm going to pick one of these. When I say that, here's one of them, here's the other one. I'm going to pick one and drop it to the denominator. But not exactly, just watch. I leave natural log of x there. I can't just put an x down here because that's not the same thing. But Matthew, can I put 1 over x?
Yes.
That's the same thing, isn't it, everyone? I'm putting a 1 over x on the bottom, which, yes, that would reciprocal back up and you would have an x up here. So I'm just getting clever in the way I'm writing things. That's all I'm doing.
Could
Just
do a -1.
rewriting it to look a certain way. Now, Matthew, this right here, where does that go? We just talked about that. Where does that go if x goes to 0? You already told me
Negative
that goes
infinity.
where? Negative infinity. Now, look at the entire bottom here, Matthew. 1 over x. And x is getting smaller, right? What happens to that fraction?
It just keeps expanding.
It gets bigger, right? So this entire fraction on the bottom is now headed to infinity. So look what we've created. Negative infinity over infinity. So we are allowed to do L'Hopital now. Isn't that clever?
Question.
Yes,
Could you have just done x to the -1 on the bottom instead of 1 over x?
yes, we could have done x to the -1, would have been the same thing. In fact, when we take the derivative right now, that's actually what we're gonna probably do. Let's do it. So now it's time for L'Hopital. All right, Matthew, you're off the hook. Jair, you're up. Thank you, Matthew.
Okay. So we take
Right
the
here.
derivative of natural log of x, which is 1 over x.
Okay, that's what the top's derivative is. Now on the bottom, be a little careful on that. This is, what's the derivative of that? Can I recommend you look at it as x to the -1? And then take the
Negative
derivative?
Oh, yes, that
To
would
the
be,
-2.
yeah,
What is it?
it would be negative x to the -2.
Yeah, and then that, could I rewrite that as -1 over x squared?
Yes.
That okay with you?
Mm-hmm.
Okay, so the derivative of the bottom is -1 over x squared. Now, at this point, you might be tempted to just let x go to 0 again, right? Just let's try it again, see what happens. But Jair, do you see that there's some algebra we can do here? Like we can flip and
Yeah.
some stuff? Okay, so let's do that. Sorry, I'm not doing L'Hopital, I'm just rewriting it. So if we flip that, the x squared goes up top, and then we'll have an x on the bottom. There will be a negative there now, right?
Yes. Can we? Oh wait, no, we can't cancel, right?
Just simplify it. Cancel an x, right? So just cancel one of the x's and you just get negative x, don't you?
Yes.
And now, Jair, what's the limit as x goes to 0?
It would be 0.
Just let x be 0, right?
Yeah.
And you get -0, which is still just
0.
0. That's the limit.
Oh wow.
All right. This is weird. I understand this is weird first time you see it. I want to go back up to the original problem. X natural log x, we are approaching 0 from the right. I'd like to graph it for you. I'm going to graph the function x times natural log x. There's the graph, okay? What we were asking is, what is this approaching as you approach x from the right-hand side? So if we come in and start walking along this, where is the graph approaching? Well, it's approaching 0, right? It's approaching 0. Now, we got that. It took us doing some work, okay? Because initially we had 0 times infinity. And please do not ever tell me that when you take a limit, that if you get 0 times infinity, do not just, if you just on a test, if you just put 0 and show no work and just happen to get it right, because it won't always be 0, okay? Then when that tells me that you don't understand what's going on here, that there's a lot involved with this, right? That you just think that 0 is a number. No, it's approaching 0. So you won't get much, if any, credit if you just give me an answer like that. So, but you can always convert it over and you can do L'Hopital. remember the limit summary?
Hmm.
Remember this thing? See the 0 times infinity? We actually now have a way of doing those with L'Hopital. But the trick is that you always have to pick one and drop it to the bottom. That's the trick. Now, when I dropped mine, right? When I picked X and dropped it down, I could have also done the natural log and dropped it. But it would have been a much harder problem. I want to illustrate that for you real quick because I just chose X. I didn't tell you why. Let me show you what would have happened had we done leave the X on top and drop the natural log on the bottom as a 1 over natural log of X. What would have happened here is that when we got to L'Hopital's rule, this derivative would have been easy. That would have been 1. But this derivative, right, when you take that, that would have been a quotient rule and it would have gotten complicated. Because this is not easy to take the derivative of. And please don't take derivative of the top and bottom. You can't do that. You have to take derivative as a quotient, so it has to have the quotient rule. All right, we are just at the tip of the iceberg for L'Hopital because L'Hopital is going to allow us to do these 3 new ones that we haven't talked about yet. Okay, and I'm going to save that for next time. So for your homework, of course, do everything in 3-3, but for the homework from L'Hopital, let me tell you what you should look at. Wow, okay. So for L'Hopital, do all that homework. Inverse trig, this right here is optional, okay? All I really need you to know for the inverse trig is what those 6 derivatives are, and you have formula sheets for those, okay? But if you want some practice with them, do those. L'Hopital, I'd say for today, we'll stop at 14. Is that good? Everyone understand?
You recommend finishing the 2.7, right? Doing all of those?
Oh yeah, absolutely. 2.7, and you have a quiz, right? I sent you the quiz.
Yep. Due by next Tuesday.
Did y'all read that quiz?
I looked at it briefly last night.
Okay. Any questions on it?
Not yet.
Well, I know last class that you said you wanted us to do like maybe 2 out of 3, but I noticed there were like 4 questions there. So
yeah, after I made it, I think it would be smart for you to just try all of them. You know, and then what I'll do is I'll just see how, you know, what people turn in. I mean, there may be some that people don't get. I might grade like, you know, the best 3 that you have or something. This is really just, I just need a quiz grade, and I'm trying to force you to actually do something with related rates because they're going to be on the test. So, you know, you just got to have practice. So. Any other questions on the quiz or anything else I've done today?
So like this isn't about the quiz, but like the next exam, do you think we're like right on like at the pace to where chapter 4.3, 2, and 1 is gonna be on the exam? And like everything.
Yeah, because we're a little ahead of the game right now, which is great. Because this is going to take forever. 4.4 and 4.5 are going to take forever. So yeah, I think we are. I think we're on track.
You had said also at the beginning that the final exam is going to be a lot more heavily geared towards the last few sections, but it'll have stuff from everywhere, right?
Well, I mean, when it comes to these problems, like for curve sketching, you need to be able to do derivatives. And within that, you have to be able to do some limits because that will require L'Hopital's rule. And Optimization problems will require, yeah, I mean, it's all kind of built in. Like, once you get to the end, the stuff in the beginning is kind of trivial, like power rule, product rule, quotient rule. That's all kind of inherent in all the problems at this point. So I don't need to go back and give you a problem and say, oh, find the derivative and I give you a product. I don't need to do that because I can ask you a word problem that requires a product rule. So it's kind of built in. Any other questions? You're free to go.
I was just saying, I mean, I've got basketball that I wanted to talk to you about, but I mean, I was waiting until everybody was done.
Yeah. Yeah, the quiz, I'm trying to remember what the quiz was. I couldn't, I made this and I completely forgot what I did. Balloon. Oh, this rectangle one's gonna be interesting. The rectangle one and the Jack and Jill one are. So let me give you a little bit of a. Like, I think number 1 and 2, those two you could probably go and Google and find problems like that somewhere, you know. The problem 3, I made it specifically about Jack and Jill, so it's hard to search for a problem like it. So I don't want you to go try and find some work that's already been done and duplicate it. I want you to think about it.
Number 2 is similar to one on the homework problems.
Yeah.
Yeah.
Yeah, I think it's number 8 actually on the homework. And you said we're free to come in on like Monday on office hours to talk to you about this.
Oh yeah, Monday is a holiday.
Ooh, that's right.
Yeah, yeah. So I don't officially have office hours, but I'll be around. So if you need me, just text me. My cell phone number's on the syllabus. I'm not quite sure what my plan for Monday is yet, but if I'm free, I'll be happy to come on Zoom.
Sweet question. On number 1, does that make a triangle, a right triangle, since it's vertically up and he walks away 10 feet from where the balloon was released?
Wait, say again?
So does the number 1, does the picture create a right triangle since where he releases it goes vertically up and he walks away 10 feet from where it was released?
Well, the observer isn't necessarily the person who released the balloon. So the balloon starts from the ground and goes straight up, and there's a person standing there watching this. And that person is 10 feet away from where it was released. But to answer your question, yes, it creates a right triangle. I'm just saying it's not like the person let it go and walked over.
Hey, Christian, this is really random probably, but do you have a sister named Savannah? I'm just curious.
No, I have one named Sydney, but not Savannah, no.
Okay, because I went to school with a Savannah Schmidt, so I don't see a whole lot of them, so.
Any other questions on this quiz?